All right, welcome back to our workshop. So hope you guys have a good lunch break, so you have enough energy to enjoy our invited talks in the afternoon. Okay, so our schedule is like we will first have a short poster session. Each paper will have a 5 minutes talk. And if the authors of the poster sessions are here in person, so you can come here to copy your slides. So we can have the oral presentation here. Otherwise, we will play the online videos. So first, we will play a short video for 5 posters. And after that, we will have our first invited talk. Okay.
For adaptive multi. Hello everyone, my name is Chen Long, and here I'm going to present our paper, Social GFs, Learning Social Gradient Fields for Adaptive Multi-Agent Systems. First is our motivations. The multi-agent systems need adaptively cope with dynamic environments, changing agent populations, and diverse tasks. However, most of the multi-agent systems cannot easily handle them. Due to the complexity of the state and task space, the social impact theory regards the complex influencing factors as forces acting on agents, emanating from the environments, other agents, and the agent's intrinsic motivations. Referring to the social force, this is an example of the social forces that affect shape and walls in a grassland. Inspired by this concept, we propose a novel gradient-based state representation for adaptive multi-agent reinforcement learning. The next is the pipeline. So first, we learn the gradient fields from examples for multi-agent systems. We use a score matching functions to train each example, obtaining different gradient field functions. For various tasks, we select different sets of gradient fields and apply them to observation to generate a gradient field-based representation. We then apply reinforcement learning base to train the adaptive agents based on that representation. By employing different gradient field functions for representation, the agent can adapt to various scenarios. Moreover, as the gradient fields are dense, they can provide informative guidance in sparse reward scenarios, addressing the credit assignment problem in multi-agent learning. And here is the environment visualization. The figure A shows the grassland game where sheep work together to collect grass and avoid wolves, while the wolves work cooperatively to eat sheep. Figure BCD are three varieties of cooperative navigation games where agents need to cooperatively reach different landmarks. And here are the baseline methods that we compare. We have team reward, reward engineering, social gradient fields, the social gradient field star, which is the adaptive model trained from the social gradient fields, and the social gradient fields plus, which is only for the cooperative navigation scenarios. We added our method designed for sparse reward scenario, the gradient field representation with credit assignment. And here is the quantitative results in the grassland games. The pairs means how many wolves versus how many sheep. And we test each method and scale the wolf and sheep reward to 0 to 1 by competing with social gradient field sheep and wolves respectively. We show that the social gradient fields-based methods outperform the other baselines. And here is the quantitative results for the cooperative navigation games. The upper graph shows the occupation rate and the bottom graph shows the success rate on the last time steps. Both the team reward method and the reward engineering method failed in the tested scenarios. The social gradient fields are only able to work in similar scenarios in vanilla navigation games. Social gradient fields plus outperforms all the other methods with a large gap in all tested environments. And thus is our contributions. We propose learnable gradient fields which are learned from offline examples by denoising score matching. For learning adaptive multi-agent policy, we develop generalizable RL-based agents to learn to act based on the gradient fields and adapt to different scenarios. We empirically demonstrate the effectiveness and generalizations of our method in both the cooperative competitive game and the cooperative games in a particle world environments.
Hello, everybody. My name is Qing Yang. I'm assistant professor in Brandley University. Today, I will represent my paper in the value-driven reinforcement learning for cooperative multi-agent system. First, let us have some background knowledge about this research. In the value describe the agent's intricate motivation, which reflect their inherent interest and preference to pursue goals and driven them to develop the diverse skill, satisfy their various needs. So when we analyze natural agents such as human, they are usually combined motivation entity. For example, we have low-level needs like the psychological needs, safety needs, and basic needs, middle-level needs, social motivations like love and esteem needs, and high-level needs like the self-actualization. Many researchers regard motivated behavior as behavior that involved assessment of the consequence of the behavior through learning expectations, which make motivation theories tend to be intentionally linked to theories of the learning and the decision making. So the computation series of the reinforcement learning addressed how predictive the value can be learned and used to direct the behavior, making a reinforcement learning naturally relevant to studying motivation. There's a big gap in current research. Although we assume each group member received the same team reward in full cooperation MAS, the benefit received by individual agents are usually significantly different according to its contribution and inner value in real-world scenario. To address this gap through integrating with the compound motivation series, we propose a novel innovative driven reinforcement learning model to describe the complex behavior in harmonious correlations. In our model, the input state and reward are generated from a critical model instead of directly coming from the environment, which means that the individual needs to calculate benefit or utility based on the inner value model or update is the current inner state combined with the external state sent into the IL model. We evaluate our approach in the StarCraft multi-agent challenge, and we implement our approach in this environment and compare the cooperative performance within three characteristics in the value agent, like coward, neutral, and recognized through the three benchmark multi-agents RL algorithm, QMix, IQL, and QTrain. And the result proves that rational organizing various individual needs can achieve the better performance with low cost in harmonious cooperation efficiently. For conclusion, we introduced the RVRL module mimic the complex behavior of the different characteristic multi-agents interaction in cooperation, and the inner value system serves as a unique reward mechanism driven agents to develop diverse action or strategy satisfy their various needs and building different personality and characteristic of the agent in their interactions. For the future direction, we list the three research area: multi-agent system, real-time strategy game, and human-robot interactions. And this is my research presentation. Thank you.
Hi everyone, today I'm going to present how to use graph neural operators to solve main-field game on graph, which models the interactions and optimal control among a large number of agents. Let's first look into one example of the game system. As shown in the figure, many autonomous vehicles are running on traffic networks, and aim to minimize their own travel cost. When the number of agents go to the infinity, the system can be captured by the decision-making of the representative agent. In this system, rho denotes the population density. The speed choice U and the route choice beta are the control of agents over the spatial temporal domain, and R is the cost. The control of this representative agent triggers the evolution of the system. To obtain the game equilibrium in this system is to solve a coupled forward-backward PDE. The forward equation is known as the FPK equation to capture the dynamics of the population evolution. The backward PDE is known as the HJB equation to capture the optimal control of the agent. As proved in our previous work, this coupled PDE system can also be reformulated into a populational MDP, as shown in the right figure. And we can use the state transition matrix as the information for the graph neural networks aggregation. To solve the coupled PDEs efficiently when the initial conditions vary, we propose a scalable learning framework using physics-informed graph neural operator called PICNO, because it can propagate information from initial conditions by projecting them into high-dimensional space. Our framework consists of two coupled modulus. The JNO modulus solves rho in the forward equations, and the HJB modulus solves optimal control U and beta. We now introduce two modulus separately. We first utilize a graph neural operator, JNO. We feed the neural operator with input fields ρ0, denoting the initial conditions. The input of the JNO is the initial population density, ρ0, along with the transition information to propagate population dynamics. The output of the JNO is the population dynamics over the spatial temporal domain, denoted by ρ0 to t. The JNO is initiated as the following MPNN. The cumulative message EIJKL indicates the ratio of population entering from edge KL to edge IG. The neighborhood message is transformed by a kernel function kappa phi and aggregated as an additional feature to estimated population density. The output of the JNO is then passed to the HJB module, which basically solves a Bellman equation regarding optimal control, given the rho. There are many numerical learning ways to solve the Bellman equation. In this work, we use backward induction, since the cost function form is known in the backward PDE. The output of the HJB modular U, beta, over the spatial temporal domain, along with the rho determined the residual to train the neural operator in the JNO modular. These two modulars internally depend on each other. Our scalable learning framework, PIJNO, can handle various initial population densities without recomputing mean field equilibriums. The initial distribution of autonomous vehicles along the route at time 0 is given. We sample ρ0 from the site consisting of various density distribution over the road network. Specifically, the right figure demonstrated the population density dynamics at mean field gain equilibrium with along 3 passes. That is the path 1, 2, 3, 4, path 1, 2, 4, and path 1, 3, 4. The results obtained by the PICNO are consistent with the results solved separately using numerical method, showing that our framework offers a memory data efficient approach for solving the mean field game on graph.
Hello everyone, my name is Qing Yang. I'm assistant professor in Brandon University. Today, I will present my paper, Edge Computing-Based Human-Robot Cognitive Fusion, a medical case study in the autism spectrum disorder therapies. First, let us have some background knowledge about this research. In recent years, edge computing has served as the paradigms that enable many research technology like AI, robotics, IoT, and high-speed wireless sensor network by connecting cloud computing facility and servers to the end users. Especially in the smart healthcare, future medical and healthcare application will involve vast amount of the real-time connected data computation and analyze, especially integrating AI and robotics technology. The cognitive robotics in the healthcare system studied the mechanism, architecture, and constraints that allow lifelong and open-end improvement of the perception, reasoning, planning, social knowledge acquisition, and decision-making skill embodied machines. And for the medical and healthcare system, the cognitive behavior therapy is a type of the psychotherapist treatment that helps the people learn how to identify and change destructure or disturbing thought pattern and negatively influence their behavior and emotions, such as the autism spectrum disorders. There are several gaps in current research area. First, smart healthcare system are dynamically flexible and complex system with unpredictable behavior and needs to organize the resources and personalize the diversity service efficiently. Second, the main challenge of the robot assistant therapy is that the model capable of the detecting the affective state of the ASD people exist and can record individual preference. So to address those gap, our proposed edge cognitive computing architecture leverage information connection and recognition, data fusion, analyze, and resources strategy optimization, human expert recommendations, and real-time therapy updating, providing higher energy efficiency, low cost, and higher user quality of the experience. We also take the treatment of the ASD as an example and propose the robot assistant therapy based on cognitive model of the human development to help the ASD patient gradually master different level of the social and communication skills. So we designed 4 specific application case representing them as a behavior tree to improve the patient's experience and enhance the effect of the RAT in different stages of the ASD. So, so conclusion of this research, we introduced a novel architecture of the edge cognitive computing integrating human expert and edge intelligent robot cooperating in the same framework to form the next generation of the medical and smart health care system. And we propose a cognitive robotic model based on CBT for ASD with the robot assistant therapies. So for the future implementation area, we want to implement in the patient monitor, senior care, and children supervising. This is my research representation. Thank you.
So we just jump to our first interactive talk for workshop. Welcome our exam AAAI fellow Sven Kinney from University of Southern California to
All right, thank you very much. Yes, so I want to talk a little bit about multi-agent pathfinding and its applications, but there's sort of a little bit of there's a little bit of sort of a lesson in there as well. So I'm from the University of Southern California, and if you look at my webpage, idm-lab.org, which stands for Intelligent Decision-Making Lab, then it says that our research focuses on decision-making for single agents and multi-agent systems to enable them to act intelligently in their environment in real time. And one of the things that we believe is that the future of AI is in combining decision-making techniques from different disciplines, because we need to create a science of making intelligent decisions. And that, of course, holds for multi-agent systems as well. And so I want to tell you a little bit about this. Now, I will do this in the context of multi-agent pathfinding, so MapF. And so I'll tell you a little bit more about this. But before I do, I need to say that we have a bunch of really highly intelligent students. We also have great collaborators who have highly intelligent students. And so lots of people did the work. I'm just the guy who's talking about it. All right, so let's figure out what this multi-agent pathfinding is. Sometimes the clicker works and sometimes it doesn't work. Good, now it works. All right, so what it is, I mean, it looks pretty boring, right? We are given an environment, and in this environment, several robots operate. We know where they are currently, and for each robot, we know a goal location. And all we need to do is find paths for all of the robots from where they currently are to their goal locations. But of course, they can collide, neither with the environment nor with themselves. And so this is an optimization problem with the objective to minimize objectives like the task completion time or the sum of travel times. When I show you some results, I'll always use the sum of travel times, and I'll call this flow time. Now, this might appear to be an easy problem, but we have heard earlier in several talks already that it actually isn't. And so we'll make some simplifying assumptions. So we take the continuous environment, we discretize that into a grid of unblocked cells white and blocked cells black. A robot will always occupy a whole cell, and then it can move within one time step to the cell immediately to the north, east, south, and west, as long as that's not blocked. And it can also stay in its current time cell. So how do we solve this problem? Well, that's pretty straightforward. I'll use the example in the upper right corner where we have a red robot and a blue robot. The red robot wants to move from E2 to E3, and the blue robot wants to move from B1 to D4. There are no blocked cells, so this is pretty straightforward. And so we can just ask ourselves, what's the state of the problem? And the state of the problem is given by the current location of each one of the robots. So the start state is A2 for the red robot, B1 for the blue robot. Right? And then we can ask ourselves, where can the robots be in the next time step if they don't collide? We enumerate all of these states, and then we can ask ourselves, will there be in 2 time steps if they don't collide, and so on. That gives us a tree. We use our favorite search method. Well, we are under AI people here, so maybe A star to search this tree, and we'll find a collision-free and flow time optimal MapF plan, and the problem is solved. Okay, so I could stop now, right? But there's a small problem, namely that the number of states increases exponentially in the number of robots. And so that's what I want to show here, right? Number of robots on the x-axis, notice it's in log scale. And then I picked sort of some environment. I picked this one here, and I'm creating 1,000 instances for it with random start and goal locations for the robots. And then I see here, what's the percentage of these instances that I can solve with a runtime limit of 1 minute each, so for each instance. And so we can see, right, that gives us the blue line here for E star in the joint state space. That's the algorithm we just talked about. And in order to compress these lines into a single number, I look at what's the largest number of robots for which we get a 100% empirical success rate, right? And so here it's 3. So we have solved the problem for 3 robots. This is great, right? Except that
she carries your purchase through the warehouse streets. This area is called the human exclusion zone, where no human may enter. There are 100 Kiva robots operating autonomously on the floor, and the Quiet Logistics crew boasts some of the fastest robots in the business. Peanut butter, butter rum, Jukebot, Bot BQ, and Walter Cabot IV. Even in heavy traffic, their sensors keep them from colliding. The server constantly monitors and coordinates.
Back into the warehouse, and that means in the warehouse itself, only robots operate. Now, in warehouses, you have this problem, then you need to store millions and millions and millions of goods, right? And so you want to be very compact. And that means that the corridors, these are these things here, these are the shelves, that the corridors are very narrow. So if a robot with a shelf moves from one side into a corridor, and another robot with a shelf moves from the other side into a corridor, well, they can't pass each other. And so that makes it for an interesting navigation problem. Before I move on, I want to point out that we see sort of white dots on the ground, and in case you have trouble seeing them, I circled some of them here with these red circles. So what they are is what Amazon calls fiduciaries. So you can view them as barcodes or RFID tags on the ground. And the idea here is that robots basically move from one to the other without location uncertainty. And you can see that they delineate cells, right? So our earlier sort of simplifying assumption actually is a pretty good fit for Amazon warehouses. So we can work with this grid model. All right, so Amazon has applications though for this multi-agent pathfinding technology or MapF technology, also in its sorting centers. Sorting centers are also in the fulfillment centers. And the idea is that once someone has put the teddy bear into a package, they put it in one of these robots here, the orange things that move around, and the robot finds the right yellow chute that corresponds to your zip code range and dumps the package into it, and that then makes sure that the package shows up at the right loading dock. Now, if we simulate one of these sorting centers, so here we see two simulations. This one here is simple, what they call traffic system. That's sort of the industry standard, and they work very simply. So for every robot, you just find the shortest path from where they are to their next goal location. And then you move the robots along them. And of course, you need to make sure they don't collide. So you use simple traffic rules like we use in our streets, like right before left, right, to avoid these collisions. And just like on our streets, I'm from Los Angeles, you see it every day, twice. You see that there is lots of stop and go here, right? There's congestion, and congestion is not good for throughput. On the right, you see a decent MapF planner where you don't have this congestion, so you can get much better throughput. Now, this is something, by the way, this looks better now. So this is basically the graph that corresponds to what I just showed to you. Number of robots on the x-axis here, throughput in terms of delivered packages to chutes per time step shown here. And then we see, if we look at the orange line, right, this is the traffic system with lots of congestion that we saw on the left. Skills as good as the good MapF planner for low robot densities. But once you get high robot density, now the congestion kicks in, right, and the throughput even goes down. And that's an issue for Amazon, because Amazon wants to run at least 800 robots in each area of its warehouse, right? And so therefore, if you develop good MapF technology, you make the industry news simply because maybe it's sort of a game changer, who knows? So that's what I want to think about in a second. But first, I want to mention that we do this research as part of the NSF AI Institute on Advances in Optimization. And I think it's actually a really interesting application to study automated warehousing if you're interested in multi-agent systems. There's the question that we want to tackle here. How should one move the robots to avoid them obstructing each other and allow them to reach their goal cells quite quickly? But then there are lots of other issues, from when should one start to process a given order? Where should one place a given shelf to maximize throughput, right? Because some items will be ordered more frequently than others. Which of several possible shelves should one fetch? And how should you place the corridors to maximize throughput, right? All of them are sort of optimization issues for multi-agent systems. And so this also validates what I said earlier, right? That you want to, for example, combine ideas from AI which is nicely applied here with optimization ideas from operations research, which apply to some of these other questions here. All right, so let's look at how we solve this multi-agent pathfinding problem here. We need to do so efficiently. We can do it for 3 robots so far. We need to scale to 800 robots, so let's do that. Now, what I will do is I will first look at optimal MapF planners, those that minimize flow time. If these are too slow, I go on to bounded suboptimal MapF planners. So those might be a user-given factor away from the optimal flow time, still bounded, so they make some quality guarantee, but hopefully run faster. And that still doesn't work. We can go to suboptimal MapF planners that make no quality guarantees, but hopefully in practice very often will have good quality. Now, first question, of course, is how difficult is the problem, right? Can we scale up? And let's look at it. So bad news, right? It's NP hard to find flow time optimal MapF plans, even on planar or grid-like graphs. And we have known this for a long time, simply because in the I classes, right, we get tormented with these sliding tile puzzles. And essentially, what we have is that a sliding tile puzzle is a multi-agent system. And not only that, it's a MapF problem if you view the tiles as the robots. Now, then there's sort of a result here that says that in some cases it remains NP hard to find bounded suboptimal MapF plans with small suboptimality factors, so more bad news. And then if we look at suboptimal MapF planning, the complexity news is good, right? Because we operate on undirected graph, polynomial time, but the quality is really bad. So that's not good because you couldn't sell this to Amazon. They need high throughput. So what do we do about it? Let's look at the optimal MapF plans, and I'll tell you sort of about my favorite planner here. Not my algorithm, but I can tell you about it in a minute. That's why I'll do it. So how do we scale this up? I'll use our example again, same as before. And it's very simple. You plan for the robots independently. Then the shortest path for the red robot from E2 to E3, and the shortest path for the blue robot from B1 to D4. And these are the paths. If the paths don't collide, you have a flow time optimal plan, you can output it, you're done. Unfortunately, in this particular case, they do collide. At time step 4, both robots want to be in D3, that's a collision. So what you do now is you resolve these collisions. And how do you do it? Well, we have a collision because both robots want to be in D3 at time step 4. So we split the situation into 2, and in one we add the constraint that the red robot is not allowed to be in cell D3 at time step 4, and in the other one, the blue robot is not allowed to be in cell D3 at time step 4. That's it, okay? Now let's look at this situation here where we impose a constraint on the red robot. Now the blue robot has no new constraint. We can just keep the path, it'll still be fine. The red robot has a new constraint, and of course that path does not satisfy it. So we replan for the red robot, find a new path, shortest path for the red robot from start to goal, independent of the blue robot. We don't look at what the blue robot is doing, but we now need to satisfy this constraint. Can use an E-star search in XYT, T for time. So maybe you find this path here, and then here you find a path for the blue robot. Now we have 2 new situations. We pick one, use priorities for that, just like E-star does. Maybe we pick this one here. If the robots don't collide, we send it out as a collision-free and flow time optimal MapF plan. Here they collide. Both robots want to be in B2 at time step 1. So we need to split again. That gives us a tree. And we search it just like with E-star with the best first search method. And eventually we will find a collision-free and flow time optimal MapF plan. So that algorithm is called conflict-based search, where conflict is just a different word for collision. All right, how well does it do? That's the green line. Okay, much better. Okay, we are pushing in that direction. But if you look at what's the largest number of agents for which we get a 100% empirical success rate, still 3. Okay, we need to do more. And so this is sort of where our work started. So we put in lots of thought, right? And we take the green line and move it to here. All right, what? Oh, yeah. Good. So I don't want to go into deep technical details, right? That's not the right forum to do it. But I want to point out that this push involved 3 different techniques. breaking symmetries. I'll not explain what a symmetry is, but let me tell you that people in constraint programming think a lot about symmetries and how to break it. You can also use more informed heuristics. And of course, people in heuristic search think all the time about how do we develop better heuristics. And you also need to avoid a duplicate search effort, meaning that these two branches, you don't do the same thing in these two branches. And people in that work in optimization, in particular mixed integer programming, have figured this out very quickly. So again, right, you can learn from different areas here and sort of think about how that applies to your particular algorithm. All right, good. So more work needs to be done here, but since we weren't so successful, right, let's go on to bounded suboptimal MapF planners. And here, fortunately, the situation is very easy because if you work in heuristic search, you know how to go from A star to a bounded suboptimal version of A star, like a weighted version of A star, or maybe a focal version of A star. But it turns out that there are very recent, very good, better algorithms out there, like explicit estimation search, that you can just put into the algorithm. Not that easy, right? But once you figure out how to do it, that moves the curves further in that direction. Now you have a dial. How bounded suboptimal do you want to be? If you want to have a bounded suboptimality degree of being only at most 1% above the optimal flow time, then you get the violet curve, right? And you scale to 400 robots. And if you can afford the 2% bounded suboptimal MapF plan, then you have the brown curve and scale to 600 robots. So this is great. We are making progress, and we are getting to these 800 robots. But I don't know whether you noticed, it was a minute runtime. Okay, Amazon needs to have that instantaneously, pretty much, because you don't want the robots to sit there idly while you're doing your calculations. So let's go and look at suboptimal MapF planners. Remember, that could be done fast before, but with really, really bad solution quality. Here you can again look at optimization, because in optimization, they have this concept of a large neighborhood search. And again, I can tell you about this in a minute, simply by telling you how this applies to what we are doing. So we find a suboptimal MapF plan without collisions. For example, using one of these bounded suboptimal algorithms. Talk about this in a second a little bit more, right? And then you pick a subset of robots that somehow interact with each other. And then you replan their paths with some MapF algorithm that finds collision-free paths with a smaller flow time. And you view the other robots, the ones that you did not select here, as moving obstacles. And then when you have more, if you have more time, you repeat this hundreds, thousands of times. And that gives you an anytime algorithm, so you can see flow time here. And so you can see that very, very quickly you get the flow time down. Now, here we needed a suboptimal MapF plan without collisions. But we can also start with a MapF plan with collisions. So for example, just pick individually shortest path for every robot. And then we do the same scheme that we did before, except that when we replan the path of these selected robots here, we do it in a way so that we find paths with fewer collisions, hopefully until we get to 0 collisions. It's not guaranteed, right? It's not a hill climbing technique. But then when we get to 0 submission, then we go back. Oops. Okay. So where were we? All right, here. So then we go back to the previous slide, right? And then we use the flow. Now, how does this work? For this environment, notice this qualification here now here, where we can do it for 2,500 robots with a runtime limit of 1 minute each. Of course, we don't know exactly what the quality is, but we have upper bounds and they look quite good. Now, let me not mislead you. The problem is not solved because we did it in this particular environment. If robot densities get very, very high, we solve the 14 puzzle or 15 puzzle, I guess, in a larger version, right? This wouldn't work so well, right? But good. So we have sort of some idea how well this works. But at this point in time, someone will always raise their hand and will say, yeah, well, this is centralized planning, right? Isn't it much better to do decentralized planning? Because centralized planning, central planner is a bottleneck in terms of both reliability, what if a robot dies, or communication, what if you have communication problems, and could, in some systems, potentially raise privacy concerns. decentralized is much better. We realize that the solution quality might be a little bit worse, right? But it doesn't have these disadvantages. How do you do this? And then I always say, well, I'm screwed because the search community hasn't really thought about this much. However, okay, reinforcement learning to the help, right? The reinforcement learning community has thought about this. If you think about DeepMind, for example, right? I mean, they've learned how to play Atari video games. So why don't we view MapF as an Atari video game, right? Where we need to get the agents as quickly as possible to their goal locations without colliding, okay? We can do this. And here we can do even better because here we have planners available in the training phase, right? Even though they take a lot of time. And so we can also learn to imitate these plans. So we can do a mix of these two and sort of warm start reinforcement learning, right? Why don't we do it? So this is how it looks like. Every action, every agent uses the same policy. The policy just determines the next action it should execute, north, east, south, west, or wait. And now the question is, what are the inputs here? And so if an agent is here, right, we assume that within a field of view, which could be really large, encompass the whole map if we want to, the agent sees obstacles, other agents' positions, other agents' goals, and its own goal. And since initially its own goal will certainly be outside of its field of view, right, somewhere else in the environment, right, we also give it a unit vector in the direction of its goal. That's it, okay? Let's see how well this works. I'll let you start these. If you could start them simultaneously, would be good. Left, a good planner, right? This mix of deep reinforcement learning, imitation learning, and this is just the plan execution. And so you can see that indeed, right? This a little bit slower, but pretty good, very good. In fact, I'm a planning guy, right? I looked at this, this is wonderful. Okay, so let me do it with 20% blocked cells. We can also start them again. Good planner here. Robots are the goals. Now they will eventually reach their goals. I would not show you a complete failure, but it takes a long time. So that suggests maybe we are not quite there yet, or maybe we are just idiots, right? I mean, maybe there are better approaches to this particular problem. And therefore, I want to look at something else here. Oops, can I go backwards? Yes. I want to look at the NeurIPS 2020 flatland competition. This was a train scheduling competition, was supported by European railway companies, and you needed to schedule trains to move from one particular station to another station. And you notice that very often you have these single track lines here, and these are just like these narrow corridors in warehouses, right? So MapF technology should apply, but there were three problems that made this really hard, much harder than automated warehousing. The scale. You started with a small problem, you solved it, you got a score for it, you gave it a bit larger problem. You solved it, you got a score for it, they gave you even a larger problem until you had to schedule thousands and thousands of trains. There was lots of uncertainty, if you could play this video, please, because trains could break down randomly, and then they remained broken down for a random period of time. Now, if you didn't react to this, we get this problem here, where there's a train coming from here, it should go here, and then this train goes down, not an issue. Unfortunately, this train, as you can see, breaks down. Now we have two trains head to head, and trains are only allowed to pull cars, not push them. You have a real deadlock situation. You would still get a score for it, right? Even if you don't get all trains to their station, but of course, a lower score than if you get all trains in. So we end at this particular optimization system here. Here's the large neighborhood search, for example, that I talked about. And here's the scoreboard in the end. So what we'll see is that the top six entries use somehow optimization technology, no learning. And then from 7 on, learning systems showed up as well. And to make it even worse, I told you that we'll have 8 hours on their server, right, where you could solve these problems, larger and larger ones, so accumulated more and more of a score, right? The curves look like this. This was the top system. And this was the best reinforcement learning system. For that, we don't have the nice curve. We only know the final result. In the end, it was here, right before it somehow ramped up. But what I want to show you here is that the top system reached the score of the best learning system after 15 minutes of the 8 hours. So there's a huge difference currently between these things. So what we learned from this is that Currently, this end-to-end reinforcement learning, especially for these rather wicked problems, is not quite there. We couldn't sell it to Amazon as a whole end-to-end learning system, but these planners make decisions. So for example, right, in the context of conflict-based search, if you have several collisions, you need to decide which one to pick to resolve next, right? And humans typically say, oh, let's try out a couple of common sense things, maybe earliest, maybe latest, maybe random one. How well this works over a set of benchmark instances, and then we pick the best one, we bake it into the planner, and we are done. How much time do you have? Okay, so in this particular case, machine learning can learn to make much, much better decisions. And that's how we use machine learning. Now I added something, that's why I was asking how I'm doing with time, because people talked about this issue of going through small gaps in the wall, right? We have seen this twice in talks, and I want to add something to it. Can you play them both? So if you look at these things, which one looks like it has more structure? Can you see a difference? Yeah, people point to the right, right? So why is this? So if you look through at this problem here, where you just have to move through a wall, right? And they color them for you. This is not our work. This is Nathan Sturtevant's work, a researcher here in Canada at the University of Alberta. The green ones, I think, move from left to right. The red ones move from right to left. What they do is they do this virtuous stigma-G that we heard about in the talk earlier, right? And the stigma-G here is they learn direction vectors via reinforcement learning. If you move in the direction or close to the direction of a direction vector, low cost for you. If you move against it, you can still do it, but high cost. And so you will see that this converges, and it gives you directions through these walls, right? So for example, this wall here is what, left to right or right to left, right to left. So this is one way of how to use machine learning as well for multi-agent pathfinding. All right, so I need to wrap up. Let me wrap up by showing you some applications of the technology. Currently, industry is very much after these things. Forklifts had more car-like dynamics. So instead of doing it on a grid, you're doing the same thing, these algorithms that we talked about on a state lattice. NASA was very interested in towing aircraft all the way from the runway to the gate to avoid pollution and keep the energy consumption, the fuel consumption low. This is done, so you can buy these food trucks, but they're human-driven. NASA wanted to automate it. Clearly a multi-agent pathfinding problem. Several robot arms that together assemble a structure could collide with each other. Not mobile robots, right? But multi-agent pathfinding problem. And this one is an odd one, pipe routing. So often, right, when a chemical plant is being built, people say you need to have a pipe that connects this coordinate with that. After we build the plant, the pipes will never change. Why is that multi-agent pathfinding? Nothing moves. But think about it this way, right? In standard multi-agent pathfinding, you have robots that move around, and they collide in X, Y, and T for time. These pipes here, completely static, but they can intersect in X, Y, and Z for height. So you can see that we can apply the same kinds of algorithms also for pipe routing. So let me stop here, right? We're going to learn more about this very exciting area. There's a web page that we created so that everybody can get started, and it contains tutorials, video tutorials, a longer version of this talk even, right? It contains, if you're a student, a class project that you can run with a visualizer where you can see what you're actually doing and create some of these algorithms. Contains publications, contains software that you can download and use for academic purposes, as well as benchmark sets. So hopefully that'll help you to get started. So let me say thank you at this point. And I know there are no questions. So I will quietly sit down, and I don't know who's next. Fast, okay. That's what I learned. But okay, for questions, I'm happy to take it on fast. we need to be all at our mics.
Yeah,
Okay.
great. Thanks for the excellent talk. Can you say a bit more about how you balance like a fast solution versus a high quality solution? Like how do you think about the trade-off between a suboptimal solution in 1 millisecond versus a great one in a minute? And does that differ between different domains like pathfinding in a warehouse versus training?
Yeah, it does. So there's no meta reasoning here, right? And the reason for this is simply that in the domain that we are looking at, right, the warehousing, you want to keep the robots busy, right? So people just say, look, what we need to do is we need to spend as much time as it takes, but eventually we need to get to real time. And that's the goal. But I completely agree that I can imagine other applications where thinking more, is a good idea. And then you need to think about the trade-off here, right? But we don't do it, right? I mean, our work here is all about how do we exploit the structure, right? I should mention that there's another problem that I didn't talk about here at all, and that is that if you want to do this on real robots, you need to make sure that the execution works, right? We AI people, to the degree that we are AI people, right? We never think about this, right? We always think that, well, plans can be ideally executed. We don't need to worry about that stuff, right? But if you do it on robots, you will notice that if you take one of these plans, put it on a robot, it will not work. And the reason simply is that you don't model effects like acceleration. So if a robot sits here and another robot comes to it, and then the plan says once they're next to each other, they can move in tandem. But of course, this guy will sit there, this comes zoomed in, this guy will slowly accelerate, and they will crash, right? So there are more problems than just sort of efficiency or even thinking about how much you should think that you need to think about.
Great, thank you.
Thank you.
Well, the comment you just made is kind of what I was going to ask, right? The mechanical engineering, robotics people say, why do you do discrete representation? You have to model velocity, course, acceleration, all this stuff. And I never have, I don't know if I have a good argument to make. So I don't know. Again, you just brought it up, the issue, but what
Yes,
is
no, I mean,
argument for this kind of
it's a good thing.
discussion?
So I got very excited, right? As an AI researcher, when one of the founders of Kiva, Pete Woolman, got up, I think he's here as well, got up at ICAPS and gave an invited talk. And the reason is that finally, right, every one of the objections that robotics researchers typically have about what we do in AI, right, doesn't apply. We can discretize it. In fact, they are already discretizing it. And usually you have location uncertainty on robotics, right? And here you don't, because you always know exactly which grid cell you're actually in. And I got really, really excited, right? Finally, we can bring to bear what we know best, right? Sort of working on these discrete structures. Now, there is some uncertainty that you do want to take into account, right? So one example is that if a robot needs to move straight over longer distances, for example, right, then what will really happen is not that it moves with constant velocity, but it will accelerate until it moves quite fast, and then it will decelerate again, and it will accelerate over several cells. We cannot handle this unless we sort of add macro actions to it. And I hate adding edges, right, because it makes the problem even more complicated, right, where it's already complicated enough. If you look at other applications, right, so for example, when we went to the forklift, we were confronted with this issue that people in robotics sometimes even discretize there, right? I mentioned sort of the state lattices, which is essentially a grid, right? Where you can say, well, with a car, right? I can turn the steering wheel to 10 degrees, right? And then I move like this. And then you wait until it hits the grid point, right? And then you say, oh, it goes from here, not necessarily to a neighboring grid point, right? But all the way to this grid point. But it means that the edges have now different length, right? And that creates a big problem, because in these algorithms, we discretize. We assume that every time step, all of the robots are at vertices. No one is at an edge, right? So that doesn't hold any longer. Now you could say, well, that's easy, right? If you have this complex edge that takes 3 seconds to traverse, put intermediate points there, right? But then again, if you do that, we get many more vertices and many more edges, and that means the technology doesn't scale. And so we needed to go from sort of something where we can just think about what happens at the vertices, right? Where we can therefore discretize time into steps, right? From one vertex to the next. We needed to think about how can we reason with time intervals, right? And then we can make them smaller and smaller as necessary. And that works. It can be put into like CBS, for example, but immediately we get a huge loss in scalability, right? We are going from these sort of hundreds of agents that I showed to maybe 10 agents.
Thanks a lot. Yeah.
Thank you. Still time? Okay, still seems to be time. If there are more questions, feel free to ask them. All right, thank you.
Next up is Chris Amato, whose most cited work is a concise introduction to decentralized POM-DPs, which is only 134 pages long.
Yeah, it's concise. We could say a lot. If we have more time, I can talk a lot about DECPOM-DPs. So I can be. Yeah, that's the next version.
Okay.
Franz and I will work on that. And yeah, and if you buy me enough beers, I will just keep talking about DECPOM-DPs. So that will also be not concise. But anyway, so this talk, I promise you, will involve DECPOM-DPs. So we'll get there. But whether that's exciting or not is up to you. I'll let you decide that later. But regardless, this talk is going to be about correcting some misconceptions about cooperative Marl. So in the title that's in the workshop, it just says Marl. I'm not going to pick on all of Marl. I'm only going to pick on the cooperative part in this talk. And I'm happy to talk more about the non-cooperative stuff if people want. Let's see if this works. Oh, before I get there, I should say, so obviously this is the work of mostly these students. They're the super smart ones that come up with the awesome ideas. All the stuff that you like in the talk is from them. All the stuff that you don't like in the talk is from me. So just appreciate the work that the students are doing. Okay, there it goes. So maybe I don't even need to do this slide as motivation. But I will say that I added this one on the plane over there, the LLM agent one, because that seems to be an exciting area for people nowadays, where multi-agent systems obviously are becoming much more widely used in lots of different applications, including what Sven was just talking about in terms of warehouse robots. But I think like one horizon for multi-agent systems is agents as whether they're chatbots or anything else, everything is going to have an agent in the future. And our agents are going to, I will never have to actually talk to Matt in the future. My agent will just talk to Matt's agent, and not in like a Hollywood sense, right? In a large language model sense. And then they will just coordinate with each other, and they'll have a great time having their beers talking about DECPOM-DPs. So yeah, so there'll be lots of these systems. I think reinforcement learning is one way that we may want to try and control these systems. And in the single agent case of single agent reinforcement learning, there's been lots of cool successes. I should update this slide, but again, like the thing that most people think about nowadays is ChatGPT, or these type of large language models more generally for successes of reinforcement learning. But multi-agent reinforcement learning is having some success, right? There are domains that are big and cool, mostly video game related things that are being solved with multi-agent reinforcement learning, but it's a much harder problem. And yeah, so it's hard for a bunch of different reasons, and I'll talk about some of them. But one of the problems is it's not even completely clear how to use reinforcement learning in a multi-agent context. There's a bunch of different ways that people tend to use reinforcement learning. And the kind of most straightforward to think about, at least, not to solve, but to think about is the centralized case, where assuming that you have centralized control as well, you can just think about it as one big agent, right? And then assuming that you have that one big agent kind of mind, right? You can just use your favorite single agent reinforcement learning method there, but that assumes that you have fast, perfect communication and yeah, only works really for the cooperative case. Or you could try and do decentralized learning and control, where each agent is basically learning separately in order to try and solve the problem. And that can work well, and I'll talk about that a little bit. But it kind of throws away some potential knowledge that the agents have about each other, and can lead to things like environmental non-stationarity, which again I can talk about later too. So what most people do for the multi-agent reinforcement learning case is centralized training for decentralized execution. How many people already know about CTDE? Like half of the room. Okay. Because I'll talk about that in more detail, definitely. So that's what most people do, partially because it's easier and it works better, where you can assume that you have like an offline situation where you can coordinate with each other. but then you have to execute in a decentralized way afterwards. So it's nice. It tries to make the best of both kind of worlds. And I will say that typically all these cases will have some form of partial observability, like we have in that kind of picture over there. Robotics cases is one particular example where you have limited noisy sensing, so the robots won't have perfect knowledge of all the other robots. And so I'll include this as well. I don't agree with Elon Musk about like basically anything nowadays, but this one I agree with him on, which he says we will do our best. Decentralized control of the robots will be critical. So for that one, I'm with you, Elon. Okay, so this is going to be the overview of the talk. So first, I'll talk about the cooperative multi-agent RL problem. That's where the DECOMDP comes in. And then I'm going to kind of complain a little bit about some of the methods, the popular methods in multi-agent reinforced learning and from the cooperative case, particularly using the CTDE methods. First, I'll talk about the ideas of using centralized critics and what current methods do and what some problems are with those current methods. And I think some relatively simple fixes that we came up with for solving some of those problems, both for the non-state case and using the state-based information. And I'll talk, if you're not sure what that is, I'll explain that soon. And then I'll very briefly, if I have time at the end, I'll mention some work that we're doing right now related to extending some of those ideas to the value-based case. So the first case is the actor-critic policy gradient case, and I'll talk about people do some similar ideas trying to use state information, and I'll talk about some possible issues there. Okay, so first, the DECOMDP slide. This is super concise, only one page. And this is the DECOMDP model. I really won't go through it in detail. I assume people get the general idea, but it's really just that we assume that we have a bunch of agents here. All the agents take an action in the environment. The environment updates based on the actions of all the agents, right? There's just one reward. This is the cooperative case. This is a joint reward that's given, and the agents get their own observations in this problem. So the idea is, because we have this joint reward, it's the fully cooperative case, and that we want to have decentralized execution. So each of these agents has its own policy, and the policy is a mapping from its own history, right? History of actions and observations to actions that it wants to take. It's not going to keep the whole history. It's going to just be a neural net, but you get your idea. Yeah, that's faster than this. So centralized training for decentralized execution has become very popular, right? So that it basically, again, is just assuming that we can train offline, and we're using this offline training phase to try and figure out what we should do, so we can just share our information. We can say, well, what if I do this and you do that? How well would we do, right? And then we could change together to try and come up with different policies and figure out which ones of those policies are the best. And then once we decide what policies to use, we can just use those policies, execute them online in a decentralized sort of way. And this has become like the de facto way of solving these, at least cooperative multi-agent reinforcement learning methods. So many of the methods that you may know about, things like MADDPG, COMA, QMix, QPlex, et cetera, MAPPO, these are all methods that do this kind of CTDE-based approach. There we go. So first we'll talk about the centralized critic-based idea, right? So the centralized critic-based idea for CTDE is to say, well, if I'm doing CTDE, right? So if I have a centralized training phase, I can also use a centralized critic. That is, if I'm doing actor-critic, the critic is just estimating the value of the policies of the agents that I have. And the actors, right, are the policies. So those things are the things that I need to act online, right? I don't need the critic. The critic is just a training construct. I can construct that during training to evaluate my policies, and then I can throw it away, and I can just keep the actors, and I use that to execute online. So it doesn't matter what form my critic could be. It could be centralized, it could be decentralized, whatever I like. But maybe I can do better using a centralized critic, or at least that was the prevailing opinion previously, right? Is that most people, starting with methods like MADDPG and COMA, right, thought that using a centralized critic would always be beneficial. You should always use a centralized critic. You should never use a decentralized critic. It's a bad idea. So we showed in these papers, and I can talk about it. I'll do a little example. I'll do a little example. in a minute. First saying in theory that they're equivalent in expectation in terms of the evaluation, so that they both give unbiased estimates of the decentralized policy. So a centralized critic isn't any better in terms of promoting cooperation, right? Because that was one of the ideas. It seems like if I have a centralized thing, the centralized thing should help me to coordinate better than if I have a bunch of decentralized things. That intuitively seems like it should hold, but it's not true. And then also the centralized critic is a higher variance estimator for our decentralized policies. So in that case, it can sometimes be worse. Now, I'll say in practice, there's some different issues that can happen based on sizes of domains and other stuff. So it winds up in practice that there's not an easy answer, and you have to actually think about it, unfortunately, as to which one you want to use, whether you want to use a decentralized critic or a centralized critic. So, so the idea of just always using a centralized critic is not the solution. You have to unfortunately think through what kinds of problem you're solving and whether it will be better to be centralized or decentralized. But I'll talk about some of that stuff as well. Okay, so so this is the more the details here, right? So again, we're partially observable, so we assume that we have some history. So these are all history-based critics, right? And actors, right? So they both take, if this works here, right? They both take as input, right? The critic takes the history. So this is the joint history, the history of all the agents, right? And the actions of all the agents in the centralized critic. And then in the decentralized critics, then this just takes the history of a particular agent and the action of a particular agent, right? And this is just estimating the value of this agent's policy, and this is estimating the value of the joint policy, right? All the agents' policies. That's the basic idea, right? And after the MADDPG and COMA papers came out, everybody basically just started using the centralized critics as a result. And so this is, maybe I'll go through this super quickly. This is the basic algorithm, or a pseudocode set of pseudocode for these kind of methods, right? That kind of shows a difference. Kind of one of the key things here that I guess in the pseudocode is not really hidden, but is often hidden in real life. That the idea here is that even in this decentralized case, where the agents are learning in a synchronous fashion, right? That is, they all act in the environment, they all see the joint reward, they all get the next observations that are based on the actions that the whole team of agents has seen, right? So in both these cases, whether you're in the centralized case or the decentralized case, this is same like synchronous time steps that are happening. So the same kind of information is getting propagated in both of these cases, right? In both these cases, the agents have to act in the world in order to get the immediate joint reward that's right that they both get, or they all get, depending on how many agents there are, right? And they all get the observations based on the underlying state, right, that you never actually see. So it's just about whether you do this kind of from your own perspective, like you do here, right? Calculating your critic and then using your critic to update your policy parameters, or whether you're doing this in a centralized fashion first, right, to calculate the critic, to update the critic value in a centralized fashion, and then using that centralized value to update each of the agents' policies, the actors. Yes, so here's an example to show what can happen in this case, a very super simple example to see what happens in the centralized versus the decentralized critic case. So here's a little game for Alice and Bob. It's a climb game, right? So Alice and Bob really want to both choose A1 so that they can get this highest return here, the 11. But there's a bunch of these issues here of getting to this 11. So for instance, if either one of them chooses A2 and the other one chooses A1, they get negative 30, right, et cetera, for these other payoffs here. So then we can think about what you would get, but if you were trying to use a centralized critic or a decentralized critic-based method for this problem, right? And so if you were to learn a centralized critic, you could learn the perfectly correct Q values here, right? You'd learn this table exactly because the decentralized critic, there's no histories here, right? So it's a single state. So you don't have to worry about histories, but then there are actions for each agent, and the critic takes as input the actions of each agent and outputs the values, right? So then once a critic's learned, if you learn it correctly, it will get the true values here. Whereas the decentralized critic will not do that. Decentralized critic, the values that it learns depends on what the policies of the other agent is, right? So the decentralized critic, in this case, if we assume that the other agent is just using a random policy, right, then it will just marginalize over each of these values, right, to get these particular values that are over here. Does that make sense, how we get this stuff? Okay, so that's kind of the key in this decentralized critic versus centralized critic idea that I'll mention again later is where do the marginalizations kind of come in? So, okay, so now assuming that we have these, right, then we got to update our actors from these critics. And the key part here is that in both cases, we have decentralized actors, right? So we have different actors, right, for each agent. So in the decentralized critic case, we use these values directly to update the actor, right? So then depending on the particular action that we're taking here, right, it's going to have a particular value, right? So, and we're going to use that to try and make this action less likely, this action even more less likely, and this action a little bit more likely, right? Based on these particular critic values, all right? So we use the direct critic values to update the actors. In the centralized critic case, we use these values again, but we have to marginalize over the other agent during this actor update because it's a decentralized actor here, right? So each agent has its own actor, so you can't just use the particular other agent action value to update your policy. So the way that it's done, right, and the way that the correct way of doing it right here is marginalizing over the other agent's policy at this point when you're updating the actor, right? So then at this point, again, we assume that the other agent's taking each of these policies 1/3, 1/3, 1/3, right? So a third of the time you'll sample this one and you'll get the 11. A third of the time you'll sample this one and get the 30. And a third of the time you'll sample this one and get the 0, right? So then as a result, what happens is given that particular policy, I'll go back, then it winds up that you'll get exactly the same gradient in both cases. You'll do the same update, whether you use the centralized case or the decentralized case, you'll get the same update, which is actually correct, which is good, because if you didn't get the same update, who knows what you would get? It would be probably wrong, right? It would be biased, it would be unsound, you would get something potentially strange. So in some sense, it's good that you get the same update in both cases, but in some cases, some sense it's bad, right? Because you're not getting the better coordination that you would hope to get by using this centralized information. And so the key is exactly what I just said. It's like just a different time of doing the marginalization, right? In the decentralized critic case, right, we marginalize over the other agent in the critic, and then we don't have to marginalize over the other agent when we're updating the actor. But in the centralized critic case, we don't marginalize when we create the critic, but we do have to marginalize when we update the actor. So it's the same math basically, but it's just about where exactly our marginalization is taking place. And so then we could show that in math, but then we could also show that in practice. We could say, okay, well, again, the assumption is the decentralized critics are always worse than the centralized critics. So maybe it's just theoretically that this is true, but in practice, it's not true. And it turns out that in practice, so these are a bunch of the common benchmarks in cooperative moral, and that mostly, as you can imagine, most of the time they do the same performance. They have the same performance. But there's a bunch of cases in which they have different performance, and usually, actually, it's the centralized critic that performs worse than the decentralized critic. For instance, like this domain here, and it usually is due to things related to the variance of the centralized critic. But we have a bunch of discussion in the paper as well about when that's the case that I'm happy to talk about in more detail if people have questions. But that's the basic idea, right? That and I didn't go into the proofs here. That was just intuition. But there's full proofs in the paper about this. They're both estimates of they're both unbiased, right, and thus correct, right? And there's more variance in the centralized critic than the decentralized critic. And we have a bunch of kind of rules of thumb as to which ones you should use in practice. Okay, any questions about that? I guess I'm not supposed to take questions during the talk. But if there are questions, you could try and ask them. Otherwise, then I'll talk about the more problematic case, which is the state-based case. So, so this idea is, okay, so we're in the centralized training for decentralized execution case, and we say, okay, so we now have this extra information that we can use. We're centralized, so we can just use simulation information directly from the simulator. That is the state. We can get the true ground truth state from the simulator that we're using for training. And then that thing is correct, right? We know where the robots actually are in the simulator. We don't actually have that information during deployment, so we can't use it during deployment, right? While agents are executing, we can't use the ground truth state. But during training, we definitely can use that. And then if we use that, maybe we can perform even better. So people decided that they love this idea. Again, this is mostly the Coma paper that I think this idea came from originally. And so people started creating these type of critics, right? Which is a purely state-based critic, right? The critic does not take the history input anymore, takes just the state and the joint action, right? The state is the joint state, right? It's the state of the whole environment. So it's the state of all the robots together, or agents together, right? But we still have history-based actors because those need to act online based on their partial observability. So those are still history-based actors, but the critic itself, now ideally, this is nice because we don't have to learn a history representation, right? So you don't have to use a recurrent network to estimate the critic. You have hopefully a concise state that helps you to learn this more quickly. So that is hopefully helpful, and it's like ground truth state. So it's like adding extra information into your training. And so then this became a popular kind of idea for people to use. So unfortunately, though, it's wrong. So unfortunately, it's unsound, and it only works in domains that are fully observable. And that's why people didn't realize this originally, because domains like SMAC are fully observable, so are nearly fully observable. And those were the benchmark domains that people tested it on. And so, and if you've worked with recurrent neural networks, they're a bit of a pain. So, the math doesn't always translate into the real world of using history representations. History representations can be hard to use. So then it turned out that the state-based critics can work well in some domains, but really are only sound for domains that are not partially observable. And I'll go through a little example to show why this is the case. And there's a very easy solution, and that is to use both the state and the history in the critic. And I can talk about that briefly as well. Okay, so yeah, maybe this is just the math behind these things, but maybe I won't go into this. It's the different critics, right? The history-based critic, the joint history-based critic, the state-based critic, and the state and history-based critic. And again, we're using decentralized history-based actors in all these cases. All right, so this is a single agent example. It got a little messy in the slide update, but I think should be understandable. So here's the problem. So that we're in some coffee shop, but we only serve coffee and tea in our coffee shop because we're cheap and we don't want to make any other beverages. So we have coffee and tea, and we need to ask people whether they want coffee and tea. Also in our coffee shop, people are very fickle, and so they don't always tell us the true value of whether it's just a toy example to try and get the point across, right? So we can ask this question, do you want coffee or tea? And then they tell us, and then we give them a particular thing, and then we get a reward, right? If we give them the right thing, and a negative reward if we give them the wrong thing, right? Yes, that's what's depicted here. Okay, so now the idea is, all right, so we're in this CTDE case where we have a centralized critic. So what we can do here is, this is history. This is our emojis of our history-based critic, right? So our history-based critic says, all right, we ask a question, we get an answer, and we can look at the value, the Q value that we get, right, of this history where we asked once, we were told T, and then the value of asking again in this case, and that will have some value associated with it, right? And then we can imagine that the value that we get on the next time step. All right, so we asked once, we heard T, we ask again, we heard T again. So basically, as you can imagine, that means that now you're getting more information, right? It's more likely that they want T, right? Because you heard twice in a row that they want T. So therefore, you have more information. Your Q value will be higher than what you had before, because now you have more information than you had before, right? And then conversely, maybe if you ask once, you get T. You ask again, you get coffee. Right now, you're kind of back to square one again, or well, past that, right? You don't know. They could be either one. So then your Q value would go down, right? And so you can do these, in theory or practice for any of these cases, right? The more that you hear the same thing in a row, the higher your value would be, because then you can give them the right thing on the next time slot, et cetera, et cetera. So this should make sense. I shouldn't say that first, because then you feel bad if it doesn't make sense. But does that make sense? Yes. Okay. All right. So what do I do for the state case? In the state case, you're kind of screwed, honestly. So the state case is you can't represent any of that stuff, right? And there's only two states. There's I want coffee and I want tea. That's it. So what happens, back to our marginalization, is in your state estimate, right, your Q value using your state, you marginalize over all these histories that you will be in when you're in that state, right? And in this case, if we assume that the agent uniform random starts in each of these states, the value of each of those states, the Q value of asking of each of those states is the same, right? Because you'll be in the same set of histories in both of those cases, right? So the Q value is the same. So there's no information gathering. Like this is the typical thing that you see in a partially observable domain. This also happens. This is, you know, the emojis are for the single agent case. This holds for the single agent case as well. We have experiments for the single agent case too. It's to say that whenever there's partial observability, you need to include history information, right? That's basically what is being shown here. And that holds for the single agent case or the multi-agent case. Yeah, so then, so the state value really, so I just have those two states. So I'm just trying to represent the value of all these, you know, exponential number of histories in these two state values. And it's impossible to do it in general. So yeah, the proofs are in the paper, but that's the intuition behind it. And so as a result, right, so this is unsound, right? So it will have bias, right? It could be it could be unboundedly bad estimate of the true Q value as a result. So then we also again tested this in practice as well to see when these things worked in practice using a history based critic, a state-based critic, and the state history critic. And again, the state history critic isn't anything particularly fancy, right? It just is inputting the state and the history in as well as the action. And so we used a bunch of the standard benchmarks, such as a bunch of these kind of smaller environments. In these smaller environments, a bunch of times the methods did about the same, but the times in which methods were better were cases where the state history critic did better than the others, which is the green line. So that makes, that's nice. And then, so StarCraft, this is the case in which the state-based critic does the best, right? So this is the blue line here. So StarCraft is the canonical set of domains in which state-based critics came to be popular. So it makes sense that they would work the best. And again, the idea there is the state, the problem is mostly fully observable. I think I have it back here, right? So that in StarCraft, you get like information from a radius, right? And everything relevant is viewable to you. So if you have a history, you're just remembering like lots of redundant information, and you have to learn to forget the redundant information. And if you're just given it directly as a state, then you don't have to learn to forget that stuff. You just have it already, right? So it makes your life easier that way. So that's the idea about why we're getting better results there, right? If you're already in a fully observable setting and you're trying to use a partially observable representation, it just makes your life harder. And so then, yeah, we see this in these cases as well. So this is these particle environments. We're adjusting the observation radius to see how much information the agents have. And there, the state history critic performs the best, right? Followed by the history critic. And then, oh yeah, this is it's just mapping a single observation to an action for the red one. And then this is the state here. And right as you, in this case, our observation radius is going up, right? Then here, the state history and the history do even better. Okay, so then this is my view of the misconceptions and corrections from these papers, because I really like these papers. I think they're super cool, but I think that the community's gotten the wrong message from them. So I'm trying to resell them from my perspective. I don't know if the authors will agree with me or not, but that's my perspective. So then, so the idea here, so MADPG kind of did two things. One is the idea of using centralized critics. And I think that's a good idea. Like using centralized critics is a good idea, at least in some cases. But again, we got to think about it. But they also did this thing where they would use policies that map just single observations to actions. And again, and that is, for my partially observable soul, it hurts. So in general, that doesn't work either. That will only work in domains that are, again, fully observable. And those many of those earlier particle environments were fully observable. So that's why they could get away with that. And so again, that will work better if you don't, it is fully observable, so you don't have to forget redundant information. So sometimes that's useful to do. But the key here is that if the environment is nearly fully observable, then using a single observation is fine, but otherwise you need to use history information. For the coma case, the state-based critics are, so they are, so the misconception is that you should use state-based critics, but they're actually unsound. The proof in coma is incorrect. Jacob is gonna update the proof at some point, but it's currently incorrect in its current form. Both of them kind of popularized this idea of using centralized critics. The idea now is that we really should think about what kind of critics that we're using here. So the takeaways of this part. How much time do I have? Am I over? Okay, I will. So I'll do this, and then I'll just mention the next part, and then I'll be done. So that we need cooler, harder benchmarks. That's number one. Because again, like if we're gonna try and be an experimental field where we try stuff and pick the stuff that works well, then we need benchmarks that are actually hard and have the properties, right, that aren't just fully observable, that aren't simple, that are complex. And I think that is what's happening with things like SMAC v2 and the Jax-Marl domains and a bunch of other stuff. So I think that is happening, but we as a community need to think about that. And we have to think about when we want to use these different things, and the state history critic often works the best. Later papers also found these kind of things, like the MAPPO. One of the stories I get from that is not just that PPO works well, but then the thing that worked the best was hand tuning the features. So the thing that was the best was the one that used hand-tuned state information and hand-tuned observation history information, and throwing away by hand things that were irrelevant to the domains, right? And that's the basic idea of just using a state and history critic there. That version of MAPPO that did the best is a state history version that doesn't have the redundant information. But more generally, like, it really opens the question about, so what should we do for CTDE, right? What is the right way of doing CTDE? And I think as a community, we really need to think about ideas that are both principled and perform well. And so I won't go into this part. I was just going to mention it super quickly anyway, but there's some similar ideas that exist in the value-based model with things like, the math got messed up anyway, with things like QMix and Qplex and Q10, et cetera, that use state information in the mixer to try and improve performance. And I'll just quickly say, the good news is the QMix and Qplex are sound. Weighted QMix, maybe not so much. But it's hard to tell because they don't have all the implementation details in the paper. And empirically, I will say the one weird result that I think is interesting is that it actually turns out that if you use other stuff instead of the state in the mixer, if you just use a random vector, if you use a zero vector, you can sometimes outperform using the state in the mixer. And I don't know why yet, but I think it's interesting. And I think, again, like as a community, we need to think about, like, what's the right thing to do here? Like, why are these things happening? And how do we should understand them, and we should try and improve them to come up with ways that make sense. So I guess that's the call for, as a community, to try and develop these kind of new principled methods, right? We should not just take whatever we see in papers as like true, right? We should really push back against these ideas, my own included, right? And really question the different methods and try and figure out why methods are working well, why do they generalize, what should we do, and try and come up with ideas that are both principled and scalable to these large domains. So that's, I will end there, maybe. Yeah, and then I don't know if Ben and I have to answer questions together. I'll answer questions about his stuff, or since he already did. Yeah. So I don't know if there's questions.
I have a question. Hi, Professor. Hi, Professor. I have a question.
Yeah.
Thank you. So in normal reinforcement learning, we were doing, grid world, cart pole, mountain car, Atari, go. And then here we saw like deck tiger, climb, So what's the,
Well, oh yeah, I'm sorry. I'll let you finish your question anyway.
oh no, so when is the magic gonna happen? Or is the magic
Yeah.
already happening and these are kind of just the corner cases that we don't?
Yeah, so I guess there's two answers to that. Like one is I take offense to being called not normal reinforcement learning, number one. And number two, so these are we tried to use like all the domains. So we tried to use like the smaller ones and the bigger ones. So like the bigger ones are like typically still like StarCraft like domains. So like these words up at the top mean like particular versions of
Right.
StarCraft, but they're still not as big as the single agent in general. They're still like the benchmarks that we use are still usually not quite as big as the single agent ones, but they're still reasonably large size. But I would argue that again, we have to be careful. Even in single agent RL, maybe I'll complain a little bit and say that I think we shouldn't just try and do well on big domains. And we've gotten a little too far into let's just do well on big domains and accept my paper because I have a better line on my big domain than you do.
My line's higher than yours.
Yeah, exactly, right? And I think we should really, as a community, be less obsessed with bigger, cooler domains and more obsessed with, I have a cool method that makes sense and it should, be able to scale to big, cool domains, but I don't want to spend $5 billion in compute to do that. So I think that should be okay. But I think they would scale, but whether they would perform super well, it's an open question.
Hi,
Yeah.
thanks for the talk. If I understood correctly, you're advocating for better ways to do CTDE, but if the way I see it from what you've talked about, you have to sacrifice to some extent to decentralize, because if you either have to give it some more observation, maybe it's neighbors locally or something, but without giving it more observation, you're not gonna go further. Or that's what I drew as a conclusion here.
Yeah, so I guess I guess in this talk I am advocating for a better way of doing CTDE, but what that means is what I guess currently right now I think people, including myself, right, are just trying stuff in the CTDE space. I think we should take a step back and try and think about, all right, well, this is the information I have during my offline training phase. I still want to execute in a decentralized phase. I don't want to like give more communication or whatever during online execution. I want to still only, execute in a decentralized way, but try and use the information that I have in the offline centralized phase in the best way possible, to really think through like what's the best way of using that. So I will I'll give an example of things that like I think could be potentially useful. Things related to doing joint updates rather than local updates. That's one particular thing. Using like in the mixers here, using history information rather than just state or random vector information. I think history information. Like so, there's a million possible things. I think people are just trying, like ourselves included, right? Just like doing. I would just want to take a step back and think more about like doing crazier things here in the CTDE phase. I don't know if that answers your question or not, but I'm happy to talk more detail, but I don't want to give too long-winded of an answer. Yeah.
Thank you.
Yeah.
Hi, thanks for the presentation. I was very curious about this result at the end.
Oh,
so this is critics that they're using history or a state.
So this is the value-based case, which I didn't really have time to go into. So right, so it's I don't know how much you know about QMix and Qplex and these methods, right? So the basic idea is that it's not a critic, right? But it's the idea that we use we learn a separate Q value per agent, and then we combine these Q values in some way to get a joint Q value, right? And the different methods have different ways of combining them.
So for history,
but they take the state information into the mixer of the Q function as a way of saying, I want to combine these Q functions, but I also want to use the state information to try and figure out a better way to combine these Q functions into the joint Q function. So it's using the state information in that offline training phase, but not in the same way as the centralized critic is.
So those results about adding like a zero vector or random vector are specific to the mixing.
Yeah, exactly.
Okay.
So that's what it is. So instead of feeding the state into the mixer, then you can feed a random value or a zero value.
I was
feed
wondering
whatever.
whether it generalized to other history representation, but it's really the mixing networks.
Yeah, so this is only think about, this result is just thinking about the mixing network.
Okay.
Like what would happen if you fed other junk in there? Like, because I think the state is not really the state anymore, but that's again a long-winded. I will have buy me some beers. I'll talk to you about that as well.
Yeah, thank you. That clarifies.
Yeah.
Actually, want to ask my question later by email.
Yeah, sure.
Let's explain.
I was wondering, do you have results on like SMAC v2 as you mentioned it? It's like a little bit more.
My student is trying to get results on SMAC v2 right now. We have results on the v1 case, but we don't have results in the v2 case yet. But we're hoping to have some very soon.
And I think like everything you said about this history really makes sense to me. And I was wondering if you have any thoughts about like simple domains with many agents. Do we always need the entire state, including all these agents? I don't think my question makes sense.
No.
But
so
because it can get very big even if it's very simple.
Yeah. Can I give a cop-out answer and just say it depends?
Yeah, of course.
Because I think it does really depend, right? Like it depends on what the domain, other characteristics of the domain. But I agree with you, like usually you don't. Like, but then like you go to like mean field, maybe if you have like too many agents. But then like I agree, there's lots of factorization probably that can also happen, but it depends on whether.
So I was wondering if there might be like critics for these problems that maybe don't need the entire state, but maybe just like, would it make sense? Just like, I was just thinking about it. So it's very like, like a rushed thought. But
yeah, no, I agree. I think that, but again, it depends on the particular cases about like what exactly you would need. And then whether you could show that that is provably correct, that it really is all the information you need, or whether it's just some approximation and then it works well. I don't know, but.
Okay. Thank you.
Yeah. I think we're out of time, right?
Like my slides. Should I move the slides with this one? Or you move it? Okay. Hello everyone, I'm Vedat from Honda Research Institute. I'm going to talk about our work called Multi-Robot Cooperative, Navigation in Crowds, a game theoretic learning-based model predictive control. So the problem that we are interested in is when the robots are navigating among humans in the scene. And there are multiple problems in this scenario when the robot cannot find any feasible path to move from
an origin to a destination, which is called freezing robot problem. And sometimes this happens when the robot and human basically end up in a situation when there's oscillatory motion among them. So one way to address this type of problem is basically using interaction between human and the robots in their motion, in a sense that robots should know how it could affect humans' movement, and then the human also react to the robot's motion as well. So, okay. So here is just a snapshot of the literature in the area of a crowd navigation, which can be categorized in two different categories. One is RL-based approach, another one is NPC-based or model-based approaches, which they consider a single robot navigating in a crowd. Another thing that we realized basically in the research gaps is that most of this works they have not considered when you have multiple robots that they need to cooperate while they're navigating among the crowd. And also when they are considering a prediction model for human, they do not consider this prediction to be coupled with the planning, in a sense that robot doesn't know how its action can affect the human's prediction. So it has been shown that when you consider this coupling between prediction and planning, you could basically solve this freezing robot problem, because now the robot is aware of how its action could affect the future movement of this human in the scene. So the way that we address this problem, or our framework, is that we have our model-based planning, and we have a deep learning based, which is used for our prediction module. And we are using social LSTM for our prediction model. But another changes that we have made is basically having this coupling between prediction and planning, in a sense that now the robot's future action could impact this planning, could impact its planning. And in that sense, we are basically planning to increase this interactivity between the robots and humans in the scene. So an example case that we are considering in this work is that these robots, they have some individual objectives. They need to reach to their goal while they are basically minimizing their jerk of their motion, their acceleration, and also they don't want to collide with other humans in the scene. And there's also this shared objective, which basically could be the robot should not collide with each other. And also another shared objective that we considered is that these robots should basically form a flock while they're moving to their destination. And we wanted to see how this affects humans' discomfort level in the scene. So the way that we solved this problem, we basically showed that this cooperation among the robots is a potential game, and interaction between the robots and humans can be modeled as two-player game, which basically the two players are a group of robot and group of human. And the way that we address this problem and solve it, we use this iterative best response, and we can basically solve this problem both in a centralized way, because the problem is now a potential game. We have this centralized potential function that we could solve, and also we could solve this using a distributed fashion as well. But we need to have a communication among the robots to share basically some parameters in order to basically achieve that distributed implementation. Here is just basically an example case where we have this flocking objective as a shared objective among the robots. And we showed that in a crowd nav basically environment, which is provided by EPFL, when the robots have a flocking objective, basically they result in lower discomfort level for humans. So human changes their path less often because of the robot's basically motion. So this is still like a preliminary result. We are planning to basically investigate this more. And yeah, thank you.
Hello, everyone. I am Samikot. I'm at the Aalto University, work in progress that I'm presenting here together with Sami Koski, titled User Models and Bayesian Decision Making for Human-in-the-Loop problems. The problem didn't fit on the line, so I removed that here. Yeah, so coming to a multi-agent system type of workshop here, my multi-agent problem is less multi than most of yours. In particular, it's 2 agents, of which one we can control and the other not really. But I hope that out of all, you guys may understand how important it is to properly formalize and model problems, because half of the solution is in exploiting the structure in the problem that you have. And so I've been looking into how to do that for these type of problems. And the unfortunate reality is that most of the time, if people try to solve these type of problems, they kind of just model the human as a black box, kind of like a source of data, most of the time in the human in the loop type of problems. And I think that's a wrong idea, and I've got some thoughts about how to do this better. Why would you want to do this? Some real world kind of applications. Consider a scientist that is interested in developing a drug, for example, for COVID, and needs to come up with kind of molecules or those type of things that might be useful in their process. Now, we actually have very, very sophisticated tools called digital twins or other types of AI methods that can replicate important processes in the real world and or optimize for certain objectives in those. For example, it's very common for a scientist to have a software program where you can say, hey, I'm interested in a drug that can, I don't know, be soluble in water, can attach to certain proteins and stuff like that. Give me a molecule. And these may be the components you can use, and these are kind of the trade-offs that we're interested in. And then these type of software, after running a day or two, will give you a set of molecules. Now, currently, most of the time, the scientists will look at these molecules, then say, it's not quite what I was hoping for, and I'm going to tune these knobs a little bit differently and run it again, right? So this is kind of like a loop, where instead of in the physical world where we experiment, these scientists will experiment with the digital twin or the digital world. And the idea here is that these programs, they don't really do anything with the feedback. They just generate the molecules according to some objective that the human has to fine-tune according to their preferences, and that's the end of it. And this is human in the loop, right? Like we have a system, has to optimize for something, doesn't know quite what, so we just allow the human to put these things in there, but we'd like to do better. We'd like to maybe infer something about the user or about the specific task that it's solving right now. And I would argue that the minimal assumptions here that we should make is that the users here in this program or in these problems, they have an objective on their own. And most importantly, these objectives are with respect to their understanding and belief of the system. So to give you a little bit of an example, here we simplify the finding a good molecule into a single dimension problem. In particular, here on the x-axis, we have our input, which may be a molecule, for example. And on the y-axis, we have a score, how good we think, or the human thinks this molecule is. And the goal is to find good molecules, right? So we want to find eventually that x is 1 is a good idea because that's the optimal, right? And this is a problem of Bayesian optimization with human in the loop, where the human is giving us the score. Now, a typical approach where you say, I'm going to do Bayesian optimization, I don't care that there's a human in the loop, I'm just going to fit, assumes that the human will return data in the way that's been described here on screen, right? So just to clarify the picture, in the light blue, the one that goes up to the right top, that is the true function that we kind of assume here that the human represents or is represented by. The axis on this line are our data we've seen so far that we assume the human would give if F here is our human preference. And then the shaded blue is kind of our posterior belief according to some Gaussian process, right? And the goal is here to pick X and learn where the optimum is. This is the assumption that we make. But if I were a human and I was interested in finding an optimal molecule or generate an optimal molecule together, I would do things differently, right? So this minimum, is this gonna work? This data point here, right? If the machine asks me what is the value of that thing, I would probably not give this data point and then later on some data point over there, because we know, or I know, that these machines are trying to optimize with me, and I want to push them in the right direction, right? So if I knew this function and everything, I would probably give data points higher score if they're closer to the optimum, just because I know that will help the system find the optimum. Right? I hope that is an obvious, or not an obvious, but the idea here. And these kind of assumptions are not being taken into consideration when we build these tools, right? We just think the human is f of x, and we don't exploit any of these underlying assumptions that we can make. Like, we have a cooperative problem here. We're trying to help. Let's assume that we have the same objective, for example. And there's been some previous work in our lab where we can show that this is happening in real life. There was an experiment here that was basically doing something like this, where the human was allowed to pick the scoring values. And you can just see that if humans, are free to pick the score according to what they want, instead of returning f of x, then then those people help the system, right? So this happens, and it's helpful. And now the question is, can we exploit this more? Can we take some of these assumptions and exploit that by doing even better? But maybe more importantly, what if these assumptions are wrong of the humans? Like, not all humans are very good at modeling these systems that they work with. So if there was some misspecification of the humans, then it may have easily been that the resulting line, or in orange, would have been below f of x, right? So we want to be able to model these things. And again, the minimal assumption here is that we are both the system and I interacting with the system are trying to do the same thing, find the optimal molecule. And we do this by trying to understand the response the system will have to our interaction. So this is all kind of work in progress, and since this poster, things have kind of progressed already. So please come talk to me if you want anything more. There's some mathematical equations there that I didn't think was worthwhile in these 5 minutes to go through, but obviously I've gone through some of the details to see how we can model this as a decision problem. Thank you.
So I think this is the final talk. And I will be covering my work on exploiting relational planning and reinforcement learning for multi-agent domains. Um, does this work? Yeah. Okay. So the basics of this project is we're trying to integrate both planning and reinforcement learning for solving multi-agent domains. And intuitively speaking, we can think of this problem just like the way humans think about doing day-to-day tasks. So um, when we want to travel to some place, for example, we want to go to a particular location, we split our thinking into high-level thinking, which is like the way we plan out our day, and our intuitive thinking, which is um, sort of coming naturally from experience. So let's say we want to drive to a place from Brooklyn to Manhattan. We're not constantly thinking about how much pressure we're going to press on the accelerator or how much we're going to turn our steering wheel, but we're just looking at the GPS and we're automatically taking turns at signals, right? So similarly, we extend this work to multi-agents by taking advantage of task-specific abstraction. So this is also similar to the book by Daniel Kahneman, where planning is the act of thinking slowly, and reinforcement can be thought of as experiential thinking, right? So so we're going to be we in this paper we use symbolic planning as the system one for our solver. So symbolic planning basically is it provides a high level plan, which is a sequence of subtasks that your agents can solve in combination in parallel to solve your goal, right? So our environment specifically are goal directed environments, and basically um, the higher level plan provides a sequence of subtasks for you to solve, and your lower level agents share these policies to perform to be performed. Um, and this is inspired by a lot of relevant work like PORL, Taskable RL by Sheila McElraith, REPRL, which is a work by our group, and so on. Um, so how this works? So this is a primer on REPRL. REPRL basically is a tree-level system where a symbolic planner, in our case a hierarchical planner, provides a sequence of goals that needs to be solved in the environment. And we used an abstraction reasoner, which are uh, abstracted representation of your MDP state, which is provided by abstracting irrelevant states using conditional influence statements or first order logic statements, followed by task-specific operators or symbolic options, which your lower-level RL agents will be solving, in our case, in parallel for multi-agent domains. So just a quick intro on how a hierarchical planner would work. Basically, if you take the task of transporting a passenger, so one of the domains we use is taxi domain. The task of transporting a passenger can be split into, or transporting two passengers can be split into its individual goals of transporting passengers P1 and P2, which can be decomposed into subtasks, in our case, which is pick up and drop. And now, if we treat this as a relational MDP, we can ground these to specific objects in our MDP, which is P1 and P2. And the relevant task-specific operators, pick up and drop, would be solving these policies. Okay, so moving on to multi-agents. Multiple agents, when you deal with multi-agent RL problems, we have the issues of credit assignment. So who solved this which agent solved this problem, right? And we also deal with non-stationarity because since there are two agents, one agent does not know the action provided by the other. We also have problems with scalability as the size of the grid increases or the number of objects increase. The problems become more and more challenging. And agents, unless they communicate with each other, they're not able to coordinate. So to handle this, we use our architecture, our framework of MA REPRL, but we're extending this to our REPRL framework to multiple agents by introducing a task distributor, And now our abstract reasoner basically is able to ground it on not just the objects for a particular task, but also the agent that needs to solve the object. And ideally speaking, if there are multiple tasks in an environment that can be solved in parallel, this can be done by using the same shared policies in the lower level, which can be done by the lower level RL agents. Um, yeah. So here's a concrete example. So our higher level symbolic planner can distribute. So this is the task of relational multi-agent taxi, which is an extension of our relational taxi domain from our earlier paper, where we are now having multiple different passengers that can be transported by more than one taxis in parallel, right? So our plan basically distributes the tasks of transporting passengers P1 and P2 um, to different taxis by both scheduling using our task distributor, and then we are using a grounded state abstraction using first order conditional influence statements, which is solved using the shared policies of pick up and drop, as you can see below. The abstract state that will be present for each of these agents would only have the relevant information of the taxi, which is doing the task of picking up the passenger. So for this example, pickup P1 and T1 would be only having information of the pickup location of passenger P1 and the taxi T1's current location. So these are our results. We've compared our approach to QMix and DQN with parameter sharing and independent learners. So we're showing success rate on the top and episode reward on the bottom, and we can see that if we're specifically using a relational MDP state where in each episode the locations of the passengers and the taxi's initial position keeps changing, we can see that we have a significant improvement in success rate, whereas other baseline algorithms aren't able to learn on its own. They're not learning exactly how to solve the problem. Similarly, we can show this for an increasing number of passengers and also increasing number of taxis, which we'll be showing in future papers. So that's pretty much our talk. If you guys have any questions, I think that's the last one. There should be one more, but okay. Is there any questions regarding the paper? Okay, thank you.
Hi, everyone. My name is Devansh Jaloda. And I'm doing this presentation on behalf of my advisor, Marco Pavone. Marco is accommodating the changes in scheduling. Some scheduling concerns. Hi, everyone. My name is Devansh Jaloda, and I'm doing this presentation on behalf of my advisor, Marco Pavone. Marco could not make it to AAAI due to unable to make it to AAAI in person. To that end, we'd very much like to thank the organizers for this invitation and accommodating the changes in scheduling and in particular the visa issues that we had last minute. So just to start off, this presentation is based on two recent works on artificial currency-based welfare programs. And in particular, I will look at the investigation of the optimal design of such systems, as well as an approach based on audit games that can be used to combat some issues of fraud in such systems. So in most parts of society, goods are really allocated to users through money or pricing, and doing so helps in achieving an efficient allocation of resources, where users generally with the highest willingness to pay end up receiving the resources. However, pricing of resources can often be perceived as being quite unfair or inequitable, as such mechanisms may end up inevitably favoring those in the higher income stratas of society. For instance, in the case of congestion pricing for traffic congestion mitigation, we know that congestion pricing has long been accepted as a means to really help in reducing some of the issues of traffic congestion on roads. But when it comes to actually applying traffic congestion in congestion pricing in practice, what we observe is that it is really met with a large degree of public opposition due to the resulting social inequity concerns, wherein low-income users typically face the burden of the longer travel times within the system. As a result, given some of these inequity impacts of traditional pricing instruments, there have been many contexts that have arisen where the use of pricing is often deemed unacceptable. In such contexts, instead of governing the allocation of resources through some type of pricing, artificial currency or credit-based systems have ended up growing in popularity, as these systems help in leveling the playing field to some extent, wherein all users are provided with very much an equal opportunity to be able to avail the desired set of resources within the system. In particular, the use of such artificial currency or credit-based systems has very much grown in popularity in the context of government welfare programs that provide support to certain eligible users in the population. For instance, food assistance programs provide users with food stamps that they can use to purchase food at food banks, thereby allowing them to avail of free food and alleviating some of their concerns in terms of obtaining food that might be too expensive to obtain otherwise. On the other hand, federal transit benefits programs are those wherein federal employees are provided with credits that are help support their monthly commuting costs to get from their home to their work. So overall, artificial currency-based welfare programs really have a lot of promise in alleviating some of these equity concerns of traditional pricing-based mechanisms. However, the efficacy of such programs often suffers from two primary concerns. First, such programs, while often being quite well-intentioned, are often really not optimized to achieve the desired or intended goals. For instance, there's often the question of whether the right amount of credits are being delivered to the right groups of people, and whether this is indeed achieving the desired equity outcomes that the program has really been designed to achieve. Moreover, beyond the potential haphazard design of such systems, another issue that hampers the efficacy of welfare programs is the prevalence of fraud. One notable concern or source of such fraud is that of misreporting fraud, which is the main type of fraud I will focus on in this talk. Under misreporting fraud, users often that are often ineligible to receive credits often misreport their private information to gain access to more artificial currency than they are entitled to. And I'll go into specific examples of misreporting fraud as I introduce this topic later in this talk, and the fact that this can often lead to a large amount of losses for an administrator that is running the program. Okay, so essentially, given some of these implementation hassles associated with welfare programs, what we do in some of our work is, firstly, to tackle the haphazard design of such programs, we first study the principal design of such welfare programs through a specific application case of so-called credit-based congestion pricing, a concept which I'll formally introduce in detail in the next few slides. In particular, what our work does in the context of the principal design of these credit-based congestion pricing or CBCP schemes is that it helps address the concern of how we can best optimize such welfare programs to achieve the desired outcomes through a principled bi-level optimization framework that we develop. Next, to combat the second issue, that of misreporting fraud, what we do is we propose an audit mechanism that can help mitigate the problems of users misreporting their private information at a low overall cost to the administrator. And the remainder of this talk is very much going to be focused on exploring these two topics and further explaining these two topics in detail. Okay, so the rest of the talk is essentially organized as follows. First, I will speak about our work on principally designing credit-based congestion pricing schemes. Then I will talk about designing an audit mechanism to mitigate misreporting fraud. And finally, I will conclude. Okay, so let's start by first talking about the more principled design of credit-based congestion pricing. So again, as I mentioned earlier, congestion pricing is very much met with a large amount of public opposition towards its deployment in practice, which has meant that it has not really expanded much beyond a few select cities across the world, with a major concern being the resulting social inequity issue where low-income users are possibly priced out of using tolled roads. This, as a result, has spurred a large amount of interest in the design of more equitable congestion pricing mechanisms, with one such class of mechanisms that has grown in popularity is that of credit-based congestion pricing. And essentially, credit-based congestion pricing does not just look at congestion pricing from the lens of tolling roads, but also from the lens of using these collected toll revenues and providing those as refunds in the form of credits to certain groups of users in the population. And crucially, what I want to reiterate here is that the refunds, and the reason why this class of congestion pricing mechanisms is called credit-based congestion pricing, because the refunds very much correspond to credits that the users are given, which can really only be used by these users to use the tolled roads and not for any other purpose. For instance, to go buy groceries at a grocery store would not be possible under a credit-based congestion pricing system, but these credits can be used to use, say, tolled express lanes on highways, for instance, right? And what I want to note here is that it is these credits in the market that very much serve the function of the so-called artificial currencies within the system, okay? Now, as a case in point of credit-based congestion pricing, in fact, San Mateo County within California, given the proliferation of highways with tolled express lanes in the Bay Area in the recent years, has launched a community transport benefits program in 2022 to provide low-income users with credits to offset some of their toll payments when using the express lane, which enables them to use the express lane for free for certain days when they use the highway. Essentially, what I want to note here is that the provision of these credits enables these low-income users to use the express lane, which they likely would not have been able to do in the absence of these credits. However, if we look closely at the current implementation of this credit-based congestion pricing scheme by San Mateo County, what we note is that it has selected $100 of toll credit allotment for users below 200% of the federal poverty limit. Now, this really raises the fundamental question of whether this $100 of toll credits is really the right amount to achieve the desired equity benefits that San Mateo County so desires, and really points towards the necessity of maybe could we have gotten a better outcome by designing these credit-based congestion pricing scheme in a more principled way that essentially delivers the potentially intended goals of this program, right? And what I want to note is that because this program is so new in that it's just launched in 2022, there's really been little work in really studying how we can optimally design such artificial currency-based systems, for instance, the credit-based congestion pricing system that has been implemented by San Mateo County. And this very much raises the important question of how we can develop some fundamental foundational framework that we can leverage to then more principally design such and optimize over such systems to really ensure that they deliver their intended benefits in practice. So to that end, what we do in this work is we study the optimal design of such credit-based congestion pricing schemes to route users on a multi-lane highway with a tolled express lane. And in particular, we have a fourfold contribution. So first, our contribution is that in modeling, in terms of we introduce a new model of a so-called mixed economy. And we do so is because we have two different groups of users in our system. First, we have the eligible users who receive these travel credits that they can then use to use the express lane. And second, we have the ineligible users who do not receive any credits, but must pay money out of pocket to use the express lane. Given that we have two different groups of users with very different objectives, I call it a mixed economy. Now, for this mixed economy, we then study the properties of the resulting equilibria, such as do the equilibria exist, and if so, can we compute the equilibria efficiently? However, what's really of interest to a central planner is not the existence of equilibria per se, but it is really about, can we design these credit-based congestion pricing schemes to really optimize some global societal objective that the central planner really cares about, that induces some good equilibrium outcomes that optimizes their respective objectives. So to that end, we propose a bi-level optimization framework to actually compute these credit-based congestion pricing schemes based on our studied equilibrium properties in the previous part of this talk. And finally, we conduct an experimental study based on San Mateo County's program and derive several policy implications. So I'll just quickly start off by introducing our problem setting. So in particular, we consider a setting where users try to access a multi-lane highway, which has an express lane that can be tolled, and a general purpose lane or general purpose lanes that cannot be tolled. And we consider a time horizon of T periods over which the CBCP scheme is run. In this case, the central planner makes two key decisions. First, what are the tolls it should set on the express lane across the T periods? And secondly, what is the budget that it should give to the eligible users in the population? And here, all users are very much going to be characterized by some value of time that they have at period T if they belong to user group G. Okay. Then in the studied mixed economy setting, we have both eligible and ineligible users with two completely different objectives, as I mentioned earlier. In the interest of time, I'll just present the high-level ideas of the differing objectives and defer the details to the paper. So in particular, the ineligible users who do not receive any credits in the system, we will assume that they minimize the sum of two terms. The first is the value of time weighted travel time that they incur in the system at each period. And the second is the amount of tolls that they spend at each period in case they use the express lane. Okay. On the other hand, the eligible users receive certain credits, that is the artificial currency that they receive. And as a result, they have a budget constraint which limits the total amount that they can spend across the entire time horizon over which the CBCP scheme is run to be able to use the express lane. And because we have these two different groups of users, where one group only receives these credits and thus has a budget constraint, the other group has no such budget constraint but pays out of pocket, it leads to different objectives of both these groups of users, and hence we call our setting a mixed economy. And crucially, what I want to note is that there has been honestly a lot of work in the transportation literature and otherwise that considers either ineligible users or eligible users in isolation. But our work really considers a setting with an amalgam of both these groups of users, and hence we call our setting a mixed economy. Okay, so given our novel mixed economy setting, what we do then is we introduce a notion of a CBCP equilibrium, which is essentially just specializing the existing Nash equilibrium notion to our particular context. And as we have in the context of a Nash equilibrium, we have that a flow pattern of users to routes will constitute a CBCP equilibrium, provided that there's no user under the objectives that I mentioned on the previous slide of the eligible and ineligible users who can reduce their travel cost through some unilateral deviation, right? So if we have such a flow pattern where no user can reduce their travel costs through a unilateral deviation, given their objectives on the previous slide, then we define that resulting traffic pattern to be a so-called CBCP equilibrium. Okay, so now the first natural question to ask here is, do CBCP equilibria exist? And if so, can we compute them efficiently? So in fact, we can answer the first question in affirmative, that in fact, CBCP equilibria do exist. And moreover, we can also show that at any CBCP equilibrium, the edge flows on the different roads across the different periods are also unique at any CBCP equilibrium. Moreover, what we can also do is we can actually show that CBCP equilibria can be computed efficiently through a convex program under a mild condition on the values of time of the eligible users. So as I mentioned earlier, it's interesting to study these equilibrium properties, but what's really of interest to a central planner at the end of the day is really about, can we optimize over these CBCP schemes to induce traffic patterns in a system that achieves some global desired objective? So to that end, and to achieve this goal, we use the machinery we've developed in the study of the equilibrium outcomes to actually develop a bi-level optimization framework to actually optimize over these CBCP schemes. So in particular, a bi-level optimization framework has an upper level problem where the central planner decides on some toll and budget combination that it wants to use, which optimizes some global societal cost function F. And given the toll and budget that the central planner chooses, users in the lower level problem best respond by forming some equilibrium, which, as I mentioned on the previous slide, can be written as a solution of some convex program, right? And so this leads to the bi-level optimization framework that's presented on this slide. Okay, so now, given our developed bi-level optimization framework, we can then perform some numerical experiments to really study how does the optimal credit-based congestion pricing scheme change in response to the changes in the central planner's objective. So to do so, we chose following simple parametric objective, which is just a linear combination of three terms weighted by some parameters lambda, where the first two terms are just the travel costs of the two different groups of users, eligible and ineligible, and the third term is the revenue. And then what we did was we investigated how the optimal CBCP scheme varies as we vary these linear combination weights lambda in the system. Okay, so the following table just depicts the variation in the optimal scheme as we vary these weights lambda. And essentially what our results demonstrate here is that the optimal CBCP scheme can in fact vary quite widely as we change the objective or these weights lambda of the central planner. And given the large degree of variability in the optimal scheme with respect to these weights, our work essentially raises a key question that is San Mateo County really achieving its desired objective through its currently deployed mechanism? For instance, its chosen $100 of credit allotments to users or not? And as a result, it has a key policy implication that maybe using a principled approach, say using the bi-level optimization approach that has been developed in this work, can actually be quite key to really fully realizing the benefits of credit-based congestion pricing in practice. Okay, and we can also just dive a little deeper into some of our results. For instance, if we look at these two particular weights of these different lambda parameters, where we fix the weights corresponding to the ineligible user travel costs and that of the revenue to be just 1 and 1, but we vary or increase the weight of the eligible users from 1 to, let's say, 11, then in this case, we observed that because we increase the weight for the eligible users, we obtain a significant drop in the revenue of, let's say, 37% in this particular context. However, as we prioritize the eligible users some more by giving them a larger weight in our objective, we obtain a 10% decrease in the travel costs of this group of users. So we can significantly improve the outcomes of these users. And moreover, the resulting impact on the ineligible users is that we have a 1% decrease in the travel costs of these other group of users. So the upshot of this particular observation is essentially that if revenue is really not the primary objective of such a system, as is the case for San Mateo County, which is giving these credits to low-income users to be able to improve their equity outcomes, then in fact, we can significantly improve the outcomes of these low-income eligible users with potentially a negative or maybe even a slightly positive impact on the other groups of users within our population. Okay, so just to wrap up on this work, what I wanted to mention was that we studied the optimal design of CBCP schemes through a principled framework of bi-level optimization for our studied mixed economy setting. And we also presented some results and numerical experiments with associated policy implications. And overall, just to wrap up, our work really points towards the importance of designing these credit-based systems in a principled way to ensure that we really fully realize the benefits of the implementation of artificial currency-based welfare programs such as credit-based congestion pricing, which we studied here. Okay, so that wraps the first part of the talk. The second part will be slightly more brief, where I'll now move to speaking about the use of audits as a mechanism to mitigate the issue of misreporting fraud in artificial currency-based benefits programs. Okay. So in this particular context, what I want to first note is that even if welfare programs have been designed well and optimized to achieve their desired goals, welfare programs are often still unable to deliver the benefits to the right groups of users due to the potential prevalence of fraud. So as a reminder, the focus of this particular part will be on the so-called misreporting fraud, wherein users that are often ineligible to receive credits may misreport their private information to gain access to more artificial currency or more credits than they're actually entitled to. And one notable case of this is that in Washington, D.C.'s Federal Transit Benefits Program, where federal employees often misreported their monthly commuting costs and monthly commuting expenses to get access to more public transit credits than they were actually entitled to within the system. And what this did was it led to over $17 million of additional credits being claimed in just 2006 alone. Moreover, in other types of benefits programs, misreporting eligibility is, for instance, often common in food stamp programs, where even high-income users might misreport their eligibility to gain access to free food. Okay, so to address the concern of misreporting fraud, what we do in this work is we design an audit mechanism wherein users signal their type to an administrator who runs this benefits program, who then best responds by deciding whether or not it seeks to audit each user, right? And for this particular audit mechanism, our contributions are twofold. So first, what we do is we characterize the conditions on the budget that the auditor or the administrator has that is required to be able to establish the existence of equilibria, which we specifically study the notion of signaling game equilibria in this work. And moreover, in the specific regime where indeed equilibria exist, what we show is that linear programming can be used to compute the associated equilibria. That is, we can compute the equilibria quite efficiently. Moreover, we can also compare the total cost of our audit mechanism to the status quo without any audits. And our theoretical results essentially demonstrate the efficacy of our proposed audit mechanism in reducing the total cost of conducting an audit mechanism relative to a setting where we don't have any audits within the system. And we also perform some numerical experiments based on a case study of Washington, D.C.'s Federal Transit Benefits Program. So just to give you a quick brief on our audit mechanism, essentially we have a game between two players, administrator and users. Each user is characterized by some true type M, which determines their eligibility to receive credits. And then the user sends some signal S to the administrator to gain access to credits. And this can very much be thought of as the eligibility information users provide to the administrator. For instance, think of this as the monthly commuting costs of the user in the context of a federal transit benefits program. Now, based on the received signal and some common prior queue that the administrator has over the user types, the administrator decides whether or not to audit the user. So if the administrator indeed audits the user, then based on some credit allocation function F, it'll issue credits to the user based on their reported eligibility if the administrator does not audit the user. On the other hand, if indeed the administrator audits the user, then the administrator can use its available budget B to conduct these audits. And each time it conducts audits, it'll incur some audit cost C for conducting these audits, right? And what these audits do is it's able to essentially enable the administrator to verify whether the signal that is sent to the administrator indeed equals to the true type of the user or not. That is, whether S equals M or not. And if indeed S equals M, then the administrator allocates credits F of M to the user. Otherwise, the administrator levies a fine K on the user for misreporting. And essentially what this slide has done is it just given you a broad overview of the interactions that are happening within the audit mechanism between the two different parties or players of our game. Okay, now for this audit mechanism, we characterize the resulting payoffs of both the users and the administrator. In the interest of time, I will not go into the details of the specific payoff structures. But what I want to note here is that both the administrator and users in our game will be assumed to play mixed strategies, where the users will play some strategy pi, which specifies the probability of reporting a signal S, given that their true type is M. On the other hand, the administrator, on seeing the signal S sent by the users, will decide whether or not to audit based on some audit probability function, sigma. Okay. Now, the specific notion of equilibrium that we're going to study is that of a signaling game equilibrium, wherein both the administrator and users best respond to each other, but the user knows its specific type M, while the administrator only knows the distribution of the types of that particular user. Okay. Mathematically, we can represent the signaling game equilibrium in the following form, where the administrator's best response given a user strategy pi prime is just given by the following optimization, wherein the administrator chooses sigma prime to maximize some utility UA, while the sigma of the administrator satisfies natural probability condition of belonging to 0, 1, given any signal S. And on the other hand, the user's best response can be computed through the following bilevel optimization, wherein a user of type M maximizes its own utility URM, while the users in the lower level, or the administrator in the lower level, maximizes its own utility as given by the earlier formulation, right? So this helps in capturing the equilibrium conditions for both the administrator and the users who best respond to each other. Okay, so now that I've just explained to you the broad definition of signaling game equilibria, what I want to note is that signaling game equilibria in general do not exist if the administrator does not have sufficient budget to audit the users. But equilibria can be guaranteed to exist in the setting when the budget of the administrator scales with the size of the largest user coalition. And in fact, such signaling game equilibria can be computed via linear programming, as is presented on the slide. Okay. What I want to note is that coalitions are typically of a small size in real-world networks, and thus our mechanism can have very much practical appeal. Okay. Beyond our equilibrium existence results, we also obtain some bounds on the level of misreporting fraud and the excess payments made by the administrator at an equilibrium as a function of the audit parameters, which can be done by investigating the properties of this linear program more carefully. Okay, and just to wrap up on the topic of our audit mechanism, another natural question we can ask is, does the budget required to run our audit mechanism really outweigh the reduction in the excess payments compared to the setting without audits? And in this setting, we can evaluate the total cost of our mechanism as being the sum of the excess payments and the budget required to run it. And essentially what we can say is that under a very mild condition, in fact, theoretically, we can show that our audit mechanism indeed improves upon the total costs as compared to the setting without audits, which we can show theoretically, as well as we can show experimentally for a wide range of problem parameters. And this includes for the setting, the theoretical setting depicted in dark blue, where our mechanisms, irrespective of different coalition sizes, has a lower cost than the theoretical optimum, but also it has a lower cost than that for the Washington, D.C.'s Federal Transit Benefits Program, which is depicted in light blue, which is the total amount of excess payments that were made for that program, right? So essentially, our results demonstrate that, in fact, our mechanism can reduce the total costs relative to the status quo without audits in general. So just to conclude this particular talk, just wanted to mention that we essentially developed two main approaches to address some of the concerns associated with welfare programs. First, I presented a work on principally designing credit-based congestion pricing schemes. And secondly, I presented our audit mechanism to mitigate the issue of misreporting fraud and benefits programs. So finally, I just hope you enjoyed this talk. And if you have any questions, please feel free to reach out to us at these emails. Hi, everyone. My name is Devansh Jalota, and I'm doing this presentation on behalf of my advisor, Marco Pavone. Marco could not make it to AAAI due to some scheduling constraints, and so he asked me to give a presentation on some of our work on his behalf. And
all right. For our final invited talk, batting cleanup, is Professor Kevin Layton Brown, AAAI Fellow, Computer Science Professor at UBC, and Distinguished University Scholar.
So I think we need to do some complicated setup because I'm just too fancy with my talk designs. I refuse to use the fonts that come on my computer. Yeah. Which just won't. So I guess I'm going till 5:20. Is that the plan?
Yeah.
Or I could just talk 25% faster than I planned. And see if we can all power through together. And
forgot to mention the most important part, CFAR AI chair, Amy.
I know, right? I remember to acknowledge it. That's where he is. All right. If anyone is watching this on Zoom, they're going to be really annoyed because you're sharing the wrong. So let's do that. Isn't technology wonderful? Okay. And I complained, hooray, yeah. And I complained about the person with the recorded talk, right? He was smooth as can be, so. Yeah. All right, brilliant. So I'm going to talk about modeling human strategic behavior from a machine learning perspective. This is sort of work in between computer science and cognitive science and microeconomic theory. Let's pretend it's an economics talk, which means you all should just interrupt me constantly. If you have anything to say, or if you feel like you could give the talk better than I could, and you have guesses about what might come on the next slides, that'd be a lot more fun, particularly since we were all just sitting here looking at a recorded video and checking our email. So, so go for it, and don't be shy. Now I have to see if this thing actually works. For God's sake, please. No. Right. So PowerPoint really didn't want me to get to slide 2 where I acknowledge my co-authors, but it's time for me to do that. James Wright is a professor at the University of Alberta, colleague of Matt's. He's my co-author on most of the projects in this talk. So way to go, James. Greg Dion, my soon-to-graduate PhD student, is in the audience here. Sophie Greenwood was an undergrad working with us on some of this work. And in particular, I should say this work, what I'm going to describe here is not a paper. It's really a line of research that we've been working on for about 15 years. I think the first paper in the sequence we published in 2010. And some of the work I'll tell you about is still unpublished. The most recent publication was that I'll actually speak about in this talk was published like 3 days ago here at AAAI, which is work by Greg and Sophie. So some of what you'll see has sort of older dates, and it'll come right to the present day. Finally, Jason Hartford is right now a postdoc in Montreal with Joshua Benju, and soon to become a professor in Waterloo. So let's go for it. Okay, there's just like a huge lag, but I think I can trust it that it's going to eventually work. Okay, so I'm sort of approaching this from the perspective of game theory, kind of the tools we saw in the previous talk, a general mathematical approach for thinking about arbitrary strategic situations. Obviously, game theory is a wonderful thing. If we didn't have something like game theory, we would need to come up with it. The reason we want game theory, beautifully shown in the previous talk, is that if we have predictions about how people would behave as we perturb a system, we can do just what we saw a few minutes ago of then optimizing over possible systems and saying which system would elicit the equilibrium behavior that meets the objectives that I have. The catch is that, of course, you don't actually get to go out and try all of these counterfactual designs and see how well they work. You just sort of simulate them in your head and then pick only one of them. And so this is all really only as good as the behavioral assumption that you're making about what people would do in all of these counterfactual worlds. And so, if you want to take, a bunch of naive users driving on roads in San Mateo, just to pick an example that comes from the top of my mind at the moment, you might wonder, would they actually reason about this financial problem in the way that game theory tells them to reason, or might they do something else? Let's think, there are many messy things about Nash equilibrium. For example, there can be many Nash equilibria, and you have to worry about which one you coordinate to. They can be PPAD hard to compute, so sometimes if the game is big, it can be even hard to find the Nash equilibria. Let's set those issues which are significant aside, and let's think about one of the simplest and strongest cases where you might want to make a Nash equilibrium prediction. That's when there's a unique equilibrium and when it's dominant solvable, which means by iterated removal of dominated strategies, you can find the equilibrium. So there's like a linear time algorithm for finding the Nash equilibrium, which is unique. So this is one of the most compelling cases where Nash equilibrium has something to say about what should happen. Let's look at what people do in situations like this. So the example is called the beauty contest game. It takes forever to explain why this is called the beauty contest game. It's not actually a very satisfying story. It comes from a remark by John Maynard Keynes that the stock market is like a beauty contest. But the way the beauty contest game works is you pick a number, an integer between 0 and 100. And the integer closest to 2/3 of the average of all the numbered picked is the winner of the game. So I'd like all of you to take a second and imagine that you were going to play this game in an internet contest that was being run by the New York Times, which I mentioned that because I want you to know the population of people you're playing with. So you're playing with the kinds of people who would read the New York Times and participate in an online contest where you get to report your answer. And so your goal is to think about what this population of people is going to do, and then to try to report the number you think is going to be 2/3 of that average. So seriously, take a second. Don't just wait for the slide to change. Think about what you would actually do. It's more fun if you do that. I won't test you, but So what's the Nash equilibrium of this game? The Nash equilibrium prediction is that this is going to happen, right? So let me very quickly walk through this, but it's probably obvious to most of you that in this game, you know, clearly no number bigger than 2/3 can be 2/3 of the, than 66 can be 2/3 of the average of the numbers reported on the interval 0 to 100. So nobody should report a number bigger than 66. But then everybody knows that. And so all of the strategies larger than 66 are just never going to be played by any rational person, right? That means that 66 kind of plays the role that 100 played a second ago, right? Because that's the largest thing anyone could possibly play. So on the interval between 0 and 66, clearly nothing bigger than 33 makes any sense to play because that's 2/3 of that interval. Or no, it isn't. It's half of that interval. So I'm not good at math. But anyway, make the numbers however it is. And then you start pushing it back. And iteratively, you can see that any beliefs that you might have, you want to undercut. And so the only stable point is to be at the bottom end of the range and to say, if I report 0, that could be 2/3 because nobody can get below me. But anything else that I believe that other people would do, I would best respond by going smaller. That logic is very easy to see. It works no matter how big the game is. I can explain it to you in about that much room. How many people in this room, by show of hands, had 0 as their prediction? Okay, so good for you. You have the courage of your convictions. You're in the right field, working in game theory, but you would have lost the competition that the New York Times held. Because here's the data that actually came in. So there were actually 61,140 responses in this New York Times poll, and so here's the histogram of the things that people did. The average of all guesses that were submitted was 28, and so the winning answer would have been somebody who said 19. So if you said 0, on the one hand, I applaud your devotion to the concept of game theory, but I also suggest that you didn't think very carefully about the fact that regular people are not every single one of them going to do that. And so if you're actually trying to predict what a population of people was going to do, it probably wasn't going to be 0. So this is interesting. So I'm going to come back to this picture later in the talk. I didn't can this. This is actually just something that when I was doing this work happened to be published on the New York Times webpage, I guess back in 2015. And I thought that's awesome. And then eventually I put it in the talk. But right now what I'd like to point out to you is just that, first of all, Nash equilibrium didn't work very well as a prediction, even in this incredibly clean case. Secondly, people did not do arbitrarily like crazy nothing, right? There's certainly some noise here, but there are also some incredibly modal predictions that people made, right? In this messy, uncontrolled experiment on the internet where people were getting no feedback when they made these answers, we see some enormous spikes. And as we go on, I'm going to claim that maybe we can explain some of those spikes, and we can have a theoretical basis for thinking about all of this that can help us to make some predictions about something like this. So overall, what I'm trying to say is many of game theory's recommendations are counterintuitive. The world is not populated just by perfectly rational agents. And if I want to make predictions about what actual people are going to do in the world rather than, say, Fortune 500 companies or something, then I'm going to need some model of how actual people behave. I'm going to restrict myself here to for the purposes of this talk, to thinking only about 2-player simultaneous move games. There's no particular reason why the methods that I'm talking about are going to be restricted only to that, but it's the cleanest thing we can think about, and we can already see the dynamics that I want to study at play in this setting. I'm not restricting myself, just to be clear, to 2 action games. I'm allowing arbitrarily big 2-player games, but I'm looking at kind of games that could be written as a game matrix. So, for example, I might say, imagine playing the game rock, paper, scissors, except if you play the action rock and win, you'll get a $2 payoff, and otherwise you'll get a $1 payoff. That's a game that you now all understand. You probably also all know how to compute the Nash equilibrium, but off the top of your head, you probably can't quite work out what the Nash equilibrium is. Then I can say, okay, Alice, what would you, I used to have a grad student named Alice. This is a perfect likeness of her. And I'd say, okay, Alice, what would you do? And Alice would say, I would play paper. And I would get that observation from Alice. And so I would kind of represent this as, I presented this game matrix to Alice, and then I observed a response from Alice that she took this action count. But of course, I don't want to do this just with Alice. I said I was doing this from a machine learning perspective, so I want to gather as much data as I can. So I'll get a whole bunch of people, and it turns out maybe Alice is not that representative of the population. Maybe most people play scissors in this situation. You know, who knows? I get some distribution of play. Now, if my goal was to predict how people play this particular perturbed rock, paper, scissors game, then I'm done, right? Then this is a pretty good prediction. But that would be a stupid thing for me to want to study. So that's not what I want to do. Instead, what I want to do is gather data about a whole bunch of different games, which might even vary in their numbers of actions, and certainly can vary in their strategic situations that they model. So imagine that I present people with hundreds of different games, and for each game, I have all kinds of different people that I observe them playing this game. And then I have this kind of data set of what people did. And what I want then is a model that predicts what players are going to do, not on these games, but on some new game. So I want to take some previously unseen game, and my model is going to, and notice this game might not even have the dimensionality of any of the games in my training set, right? This happens to be a game with a larger number. So I'm always going to be asking about player one, right? So just as a convention, right? So I have more actions here for player one than any of the games in my training set even had. I still want my model to be able to say what it thinks is going to happen. And then my population actually did something on this game that, I had held this game out from my model's training. And then I want to evaluate how my model did as compared to all of these observations that I actually made. So as luck would have it, there's a bunch of really smart people in the experimental economics community who have gathered data like this. So one reason we restricted ourselves to simultaneous move two-player games is that many smart economists have gone to a lot of trouble to gather data about this very thing. And gathering this data is no small thing, because you have to get a population of people into a room. You have to incentivize them to actually care about the payoffs of the game, rather than, for example, caring about getting a bigger score than the other player. You have to set it up in a way where you make sure they understood the game, and you make sure that they aren't thinking of it as a repeated game, but they're thinking of it as a one-shot game. And you have to, basically the way you incentivize them is you pay them money in proportion to how they actually did in the game. So these are expensive trials to run. And then you make a bunch of observations. So what James and I did is we kind of crawled the economics literature, and we made a giant meta data set out of everybody else's data. Even though all of these populations of people were different, the only thing we really did to rectify the data was to put it all into the same units. So we normalized it so that it was kind of all in expected dollars, and otherwise it was just what it was. And this gave us a data set that had like 128 different games and thousands of observations. So not enormous by kind of deep learning standards, but enormous by behavioral economics standards. And then we want to think, how well does a model do here? And amazingly enough, when we started this work, and I think almost even today, almost nobody in economics takes this approach of taking their data. So all of these models, spoiler alert, that we're going to end up fitting are going to have free parameters. And so we're going to have to estimate these parameters from training data, and then we're going to have to take this fit model and evaluate it on something. And virtually every paper that I cite here, and I think virtually every paper that has been written in economics on this, has reported just training set error, which is really a shame. So one thing we kind of tried to persuade economists of is that they should do a training test split, where they fit their parameters on the training set, and then they evaluate the quality of their fit on the test set. And then, of course, we do this multiple times, cross-validating across splits, because we have a small amount of data. So the previous slide said, we should, evaluate loss on the training set, and then, minimize loss in the training set, and then evaluate loss on the test set. What should this loss function be? It turns out that the behavioral game theory literature has not settled on a single loss function that they consider to be best. Some people, including my own work with James that I'll be serving in this talk have used log likelihood. Other people have used error rate. Some people have used Breyer score. Some people have used squared L2 error. Other people have used yet other things that I won't talk about here. I'm going to use negative log likelihood because some of the computational experiments that we ran were really computationally difficult to run, and we haven't rerun them yet. But James and I were always really unhappy with the fact that we were using log likelihood because its units are uninterpretable. You can't look at some log likelihood scores and get a good sense of whether you're doing a good job. And it doesn't give you any sense of whether you're close to perfect prediction. So for a long time, we've been kind of banging our heads against the wall, trying to think about whether there was something better we could do or some principled argument that could be made about whether one loss for this problem of evaluating behavioral models might make more sense than other losses that we could use. And we basically had to wait until Greg and Sophie came along and finally did a beautiful piece of work that they presented, I guess that Greg presented here at AAAI a few days ago, arguing from an axiomatic basis which loss function is the right one to use for this kind of a study. And that was a whole AAAI talk by itself, so I'm not going to re-give that talk here. But that work argues that behavioral game theory loss functions, or more broadly, any machine learning approach that wants to study behavioral data, where you have a model that predicts what happens in different treatments, and where in each treatment you get to make multiple observations, not just one observation, because you're trying to predict something about a population. It says that you should have to satisfy a set of 5 axioms. And sort of broadly speaking, this looks similar to the scoring functions literature, if you know about scoring functions. But a lot of the time when people are thinking about scoring functions, they're not thinking about this multiple prediction case. And another thing that people are often not thinking about in this kind of scoring function setting is the idea that your model family might not be able to perfectly represent the concept that you're learning. And so you might have to be satisfied with sort of approximate fits to your data. So we have a couple of axioms that generalize versions of the propriety, the notion that you should have a proper scoring rule. Those axioms from the scoring rules literature to the case where the function might be misspecified and the true minimum might not be expressible by the function. And then we also have some interpretability axioms that say you should be able to look at the actual numbers that are coming out of your loss function and make some sense of them. So if you imagined varying the underlying distribution of observations, you should know what would have happened to the score. A perfect prediction should have gotten 0 loss, so your things are normalized. And your loss should be independent of permutations of the observations. It shouldn't matter what order they came in, and it should be independent of the number of observations. So you should care about the shape of the empirical distribution, but you shouldn't care about the count of the distribution. And when you put all of that together, and you look at all of the loss functions that people in the behavioral game theory literature have actually used, you find something kind of surprising, which I promise we didn't set this up to work out this way, but this just turns out to have been true after a almost 10-year project of trying to come up with the right axioms. That almost everything that people are using in the behavioral game theory literature has some flaws with respect to these axioms. And there's, by coincidence, only one thing that people have been using that satisfies all the axioms. It turns out our paper is not a characterization that says this is the unique thing that you should do. It rather identifies a set of things that are consistent with the axioms. And there just happens to be one thing that people have been using so far, which lies in the broader set that we've identified. Which we call diagonal bounded Bregman divergences. So it turns out the squared L2 error is an example of a diagonal bounded Bregman divergence. You might be wondering, you see sort of success and failure for some of the loss functions, and then you see these weird warning signs. Those are cases that mostly work, but that have infinity conditions when zeros get reported, and they can break in those special cases. You might, so you probably know that log likelihood blows up if you predict that something happens with 0 probability and then it actually does happen. You might think that's a boundary case that we shouldn't worry too much about. So you might think log likelihood isn't so bad after all, except that it's really uninterpretable. But that's actually a bit of a problem in the game theory context, because game theory makes zero probability predictions all the time, right? Actually, we just saw one of them in the yeah. Let me finish the sentence. We just saw one of them in the beauty contest game where Nash equilibrium really just did predict one thing. Yeah. Oh yeah, right. Because we're predicting distributions here, right? Thanks for coming to the talk, Greg. Usually it's bad form when the advisor answers the questions and the students giving the talk, but I think the other way around is totally fine. So awesome. So as I go on through this talk, and this is the first one you'll see, but not the last one, I'm going to identify what I think are open research questions that people should be thinking about in this space. So if you think this work is interesting, here are some things that I don't know the answer to that I would invite you to think about that kind of get flagged as we go along. I'm going to have 9 of them throughout the talk, and now we're building up steam, so they're going to start coming quickly. So the first one is, what loss function should you use? So if I was going to do this project today, I would use squared L2 error because I don't have an argument against it, and people have used it before. But that's not the most compelling argument you could hope for. And I've got to essentially, I've expressed sort of an equivalence relation among a bunch of loss functions. So you might wonder if there are additional axioms that should narrow things down further. And you might also wonder, if I reran some of the experiments that I'm about to show you in a minute, how things would be different if I actually followed my own advice and used squared L2 error. And you might also wonder some of the conclusions that I'm going to be drawing throughout this talk, how much more interpretable they would be if I use something that was more possible to interpret. So all of that TBD. So now we've, after much ado, we've figured out how you might score a model prediction on behavioral game theory data. What procedure should I use for actually fitting this thing? It's a bit of a funny machine learning problem. It isn't a simple classification, because I want to return a probability distribution over player one's actions. I don't just want to pick something. But it's also not straightforward density estimation, because I want to be given a game of arbitrary size and return to you a distribution over however many rows there were in the matrix. So I want a 2-dimensional object back if you give me a 2x2 game, and a 3-dimensional object back if you give me a 3x3 game. Overall here, the models that I'm looking for are mappings from games to probability distributions. And that just doesn't directly pattern match to the most obvious machine learning things you could do. So when I think about sort of what my baselines should be here, the most obvious kind of off-the-shelf set of baselines come from the discrete choice literature. So you can look at like logistic models or mixed logic models that essentially score every action separately and then normalize by these scores and predict a distribution in proportion to how much they like these scores. And you can do it with a single logistic, or you can do it with this sort of multi-factor model with 10 different latent classes here. So this is kind of, I'm not meaning to suggest that this is a particularly brilliant thing you could do, but this is an off-the-shelf thing that you can do. And so here's what happens when you do it. So I'm going to show you on the right a box plot of training loss, because that's what economists think about, but don't look at that unless you want to assess overfitting. And on the left here, not grayed out test loss. And it's a box plot, so red is the median. I'm showing you how much variation across cross-validation folds I had in the error to give you some sense of stability. And you can see I'm getting a bit of a better fit from mixed logic and also less variance than I am from logistic regression. So that seems like a good thing. Yeah, I could play with how many classes. I didn't do that. I just had 10 classes. And it seems, I'm actually fitting something both in the test data and in the training data. So I'm not overfitting with the 10 classes. But is that any good? Like, what do these negative log likelihood numbers mean? I'm trying to, like, it's sort of tempting to want to know about accuracy, right? But think about this rock, paper, scissors game. You know you should be playing a mixed strategy. I'm seeing samples from one mixed strategy. Are they the samples I should have wanted to see from a different mixed strategy? Like it's hard to compare these numbers when the underlying objects really should be probability distributions. So one thing we can do is say, what if I just always predicted the uniform distribution? How much loss would that have? And basically, if I can't beat that, that's like a 0 parameter model that knows nothing about the setting, then I'm really not doing very well. And so we actually see here that logistic regression is nailing it on the training data, but it's overfitting the training data, and it's actually doing worse than the uniform prediction on the test data. So that's really, really bad. And mixed logic is a bit better, but it's sort of hard to know what these units mean. So enough of that. Let's say something about behavioral game theory. So behavioral game theory has proposed a bunch of hand-tuned models that are based on cool ideas from psychology. And here's a bunch of the most famous models from behavioral game theory that are applicable to this simultaneous move, unrepeated setting. And James and I have kind of thought about this work and tried to kind of unify it. And the way we tell the story, all of this work, I'm not going to tell you what all these different models are, but they all are basically based on different instantiations and combinations of 2 key ideas. So I want to tell you what the 2 key ideas are. And so we call them quantile utility maximization and iterative strategic reasoning. So second research question you might want to think about, are there other general psychological insights that we should be thinking about besides these 2? Quantile utility maximization is easiest to understand when I contrast it with best response. So best response says, imagine that I give you 3 options. You can get an expected payoff of $1 and a penny, an expected payoff of $1, or an expected payoff of $0.25. What should you do? And you would say, I'm no fool. I'm going to take the biggest number. That sounds like the best thing for me to do. Quantile utility, quantile response is what people in AI would think of as a softmax. So it says, I like bigger numbers better than I like small numbers, but I've got some sort of noise in the way that I maximize something. So I would take the biggest number the most often. I would take a number that's very close to it almost as much. And I would take a much smaller number, not never, but way less often. And quantile response has a parameter in it that says, how sensitive am I to utility differences? So this is one parameter that I might have to fit. Iterative strategic reasoning is based on the idea that we do think about how other people will play, but we don't necessarily go all the way down the rabbit hole. We might just sort of stick our head in the rabbit hole some depth. And so iterative strategic reasoning is grounded in the idea that there are some people in the world that we can call level 0 people. And level 0 people are people who don't think about other people's play at all. They just do something. And they are most often in the literature modeled as just playing uniformly at random across their options. And economists that have talked to me about this believe, as a matter of religious conviction, that level 0 people don't really exist. They're just a fiction that people have in their heads so that they can think about the rest of what I'm about to tell you next. We'll revisit that point, although it has led to some very sad responses to reviewers in economics publications. But level 1 people are people who are kind of one step smarter than level 0 people. So they believe that the world is full of level 0 people, and they're going to get the jump on them. And so if they think that a level 0 person would play rock, they would play paper to beat rock. And of course, you can see where this is going to go. Level 2 people are 2 steps smarter than level 0 people. They best respond, or quantily best respond, as the case may be, to people either the level below them, or maybe they know the true distribution of people in all the levels below them, and they respond to that distribution. This is why we have this sort of whole family of different models. And so we can keep on going up to some level K who respond to the level K minus 1, but we're going to ground this out at some finite point. So you can see kind of Nash equilibrium as iterative strategic reasoning to arbitrary depth, and then claiming that everyone's going to be there. So this is kind of a relaxation of that idea. And now let's come back to this graph that I promised you we would come back to. And that now, which I promise, I didn't even vote in this game, so I really didn't perturb this data at all. But it's such a beautiful found example of something that we know to be true from the cognitive science literature. So let's begin by noting that there's a spike at 50. That does not make a lot of sense. If you think about why, if you're playing the guess 2/3 of the average game, that you would think that people are going to be, every single person in the world, is going to be averaging out at 3/2 of 50, right? That 75% is going to be, incredibly popular. Although, it does have a little but I would say that you're not doing a great job of thinking about other people's preferences if you're guessing 50. So I think those must be level 0 people. And if they are, then it's interesting that at 2/3 of that number, there's an enormous spike. And in fact, at 2/3 of that number, there's another big spike. So that's pretty amazing, right? It really does seem like some kind of leveled strategic reasoning, is happening in this data. And we can go on. If you look up here, the people who said 100, I'm going to argue that they definitely are level 0, right? Because that's not 2/3 of anything. So you're really, you might not even be thinking very well about the game, but you're certainly not thinking about other people's play of the game. And then if we start, iterating back again, here are some people, once again, who are 2/3 of that, and some people who are 2/3 of that. So there might be sort of various inconsistent level 0 beliefs that people have, to which people can do level 1 and level 2 reasoning against it. And we can go on, but that's most of the modes. Yeah, please. What a good question. As it happens, remember that data set I told you about where there were people who were incentivized by behavioral economics researchers who put money on the line and tried to incentivize them using, rigorous standards that, they got ERB approval for. And what if we took this model and tried to fit it on that data? How well would it do? That's the best way I know of answering your question. And it does very much better than the logit models, even though this is a 5-parameter model. So that seems like a pretty good win for behavioral game theory. And this is on a hard problem, right? This is on the problem with way too little data of training on one set of games and then evaluating on entirely different games using a 5-parameter model. So I think you've captured, this is clearly not the last word here, but you've captured something about how people reason in games if you're able to do that, I think. And, definitely the random guessing line is, way in the sky. So, bear in mind, this is negative log likelihood. So this is an exponential scale, right? So we thought that was pretty cool. Then we did a Bayesian analysis of the parameters that this model was fitting. And we were finding something strange. We were finding that our model predicted that the biggest group of people were level 0 people. And this said that our best performing models were quite certain that a lot of people were randomizing uniformly over the actions. And that doesn't seem behaviorally plausible to us. And so we saw this as likely evidence of a misspecified model, that all it could do to capture some of the play was to just put a lot of weight on uniform randomization. And so incidentally, a question that this throws off is whether we can fit models in a way that better constrains the parameters to their intended interpretations that economists would like them to have. But this made us think a lot more carefully about level 0 behavior. So we thought, why should level 0 agents only be allowed to uniform randomly? Why don't we make another set of model parameters that describes the play of level 0 players? And then we fit the whole thing so that the level 1, 2, 3 agents are best responding to beliefs about those level 0 agents rather than the crazy uniform people we don't really believe in. What if we took seriously the idea that some people really don't behave strategically in the world? But when I say they don't behave strategically, I don't mean they just do complete garbage. I mean, they do something that doesn't involve thinking about the other players in the game. They look at the game kind of as though it was a one-player game, and they do something that doesn't involve forming beliefs about the other players. And then we have a second group of people who do form beliefs about such players, and they have this kind of leveled response. And we wondered, can you do better with a model like that? And there are many ways you can do it. It turns out QCH is pretty hard to beat. So we tried many things that didn't work, and this was the thing we tried that was the best. So we had 4 binary features that say about each action something, it either fires or it doesn't fire. You might wonder, should they be real valued? We thought they should be real valued. We couldn't make that work. Open question number 3.5. But we said, is this action best in the deterministic worst case? Does this action contribute to my own highest payoff outcome? Does this action contribute to the least unfair outcome in the world? And if the game is symmetric, is the game symmetric? And if so, would this action be best if my opponents copied my strategy? Both things have to be true for it to fire. We tried all kinds of other features too. These are the ones that helped us. And we then say a feature is informative for a game if it distinguishes at least one pair of actions. So if it fires for everything, it's not informative. It fires for nothing, it's not informative. And then we say if a feature is informative, then we're going to give it a certain weight, and we're going to learn the weight. So we're going to give that weight to the action, and we're going to learn what those weights should be. So every action is going to have a prediction which is proportional to kind of a base weight, which we learn, and then the sums of all the weights that fire. So that's our level 0 model. And when we fit that model, we got a prediction that's much better. I'll show you something on a coming slide, but this really is a big improvement because this is an exponential speed up. So this is a 10 to the 20 times likelihood improvement over our previous model. It just looks less impressive than it is because I have uniform guessing at the top here. Yeah. No, what these models would do would be to sort of learn the average across all of the modes, right? So it would just try to predict like the ex ante level 0 play across all of the modes, and there's nothing stopping it from doing that, but it isn't gonna, there's no way that it would think about which kind of, there's actually really no sense in which you're even modeling specific people, right? You're just sort of thinking about the distribution of play. So some of our level 0 models could be rich enough to learn multimodal distributions, and that's what they would do. Yeah. Another excellent question that will be answered, I think, possibly on the next slide. So let's do it. So a better model of non-strategic play made a big difference, but it's 2024. Like, why am I making up all of these features? It seems like I might prefer to do some kind of end-to-end thing where I try to learn the structure from the data. And so that was our question. Can we find some kind of over-parameterized architecture where we can do feature learning out of the gate here? And notice that this is a bit of again a funny machine learning problem. I want to make sure I have a model that has the right equivariance properties where I can deal with game permutations in the right way. I want to have this weird variable size output where I'm returning a distribution of whose size depends on the size of the input. And I want this thing to be rich enough to model iterative strategic reasoning because I already have pretty good evidence that that's working for me. So another long story short, this is a paper we presented at NeurIPS 2016 before graph neural networks were a thing. At this point, you could do something similar with graph neural networks, but it doesn't really morally change the story that I'm going to tell you. But basically, we came up with a way of having the right equivariance properties, building a big, complicated level 0 model, and then kind of tacking on a specific architecture that has some parameters that could explicitly model level K reasoning. So kind of, this big soup right over here is all kind of level 0, sort of flattens out into a level 0 prediction, and we have a few more nodes that have parameters for thinking about each of the subsequent levels. And when we learn that, we look at this thing. Now I'm going to show you all of this on a graph that isn't blown up by random guessing, so we can see a little bit better. So here's QCH against a uniform level 0 model. Now I've zoomed in enough that you can see the error bars from cross-validation folds. Here's how much better we did with our linear 4 model that I told you about just now. And here's how we do with different sizes of architecture in this deep learning architecture that I just told you about. So you see evidence of overfitting on the right. So at some point, we only have 3,600 observations of human play. So at some point, when I'm learning a 300 parameter model, 3 layers deep, 100 parameters per layer, we started to overfit. But before that, we're doing well. So we're improving, all the way up to a 2-layer 100 by 100 model, and we're getting a pretty substantial improvement in predictive performance, bigger than the gains that we had from the level the previous handcrafted level 0 model. But there's a sad thing, which is that the action response layers were completely useless for us. We found no marginal gain from adding them. We just did this by predicting absolutely everybody as a level 0 player. Or was it a level 0 player? I mean, we called it a level 0 player, but now it's this like crazy, like 200 parameter model. At some point, when you don't really understand what level 0 play is doing, is it really reasonable to call this level 0 play? It's able to do all kinds of stuff that we don't really understand. It's a universal function approximator, sort of discretized to a certain point. So this started to make us unhappy about our and we started getting like pointed questions from people at conferences about, why are you calling this non-strategic behavior? Like, how do you know? And if you know James, you know that James loves to go down a rabbit hole. So we started thinking really carefully about this question of like, what's non-strategic behavior anyway? What should we allow ourselves in a level 0 layer? And we have an answer. Like, we know what we want the answer to be. We want the answer to be that you're non-strategic if you're not modeling other agents, and you're strategic if you are modeling other agents and responding in some sense to those beliefs that you have when you do the modeling. But that doesn't describe a behavior, that describes a procedure, right? So when I have some crazy neural network, it's very hard for me to know whether what it's doing amounts to both modeling other agents and responding to them, or if it in some sense really isn't doing that. And so it's hard to know whether this thing could sort of be rephrased in strategic terms, even though we sort of tried to have it not be doing that. And we recently, in a paper that's still kind of under R&R at the Journal of Economic Theory, have a new formal characterization of non-strategic behavior that, if you care about the distinction between strategic behavior and non-strategic behavior, I would encourage you to look into, because it's actually a positive result that says, here is a broad class of behaviors that I'll tell you about on the next slide, that are, in a really formal sense, provably non-strategic, even though they're really rich. And then strategic behavior, which is modeling and responding, is separable from this in a precise sense. And this allows us to have a big set of parameterized behaviors, all of which we call non-strategic, and then to optimize over it and fit something and know that we kind of haven't smuggled something in. So how does this work? The core idea is something that we call elementary behavioral models. And the idea is, given a game, I want to learn some potential function of this game that is applied point-wise to every element of the game. So I take this, conceptually, this 2 by 2 or n by n, or n by n, or like n by n by n, whatever. I take this matrix that has multiple values in every cell, and I boil it down using an arbitrary function into another matrix that has only one number in every cell. And I do this, the function can be anything, but I have to apply it element-wise. So I have to apply the same function to every cell of the matrix. And this function is basically unconstrained, except it has to be no smuggling. And what we mean by no smuggling is you can't do stupid real analysis junk where you just pack multiple real numbers into one real number by just kind of doing bit encodings. So we want that, in a mathematically sensible sense, you really do have to come up with a single number. And the definition is technical, but I'm happy to talk about it. Then once you've got this one-dimensional matrix, you then can do whatever you want to it. You can compute its Nash equilibria, you can run it through a mixed integer programming solver, you can do what you want, but you're forced to have lost information. And this is meant to capture the intuition that like a level zero, one thing a level zero agent might do is respond only to their own payoffs. Another thing they might do is only respond to somebody else's payoffs, right? Another thing they might do is they care only about fairness. So they take the sum of everyone's payoffs and then they respond to the sum. So there are lots of things that a level zero player might do that involves kind of flattening the matrix down into some concept and then trying to maximize something in that concept. But they don't get to like compute Nash equilibria or something where they think, you know, in a really rich way about both people's payoffs. And we prove that no existing strategic decision rule like Nash or quantum response equilibrium or any of the behavioral models that we have is elementary. We prove that no elementary model is strategic. Neither is the linear 4 model that we used. And in a really recent result that we had in response to some reviewer feedback, we discovered that the deep learning model that I just showed you is strategic by our definition. We actually thought it was non-strategic, but it isn't. And so maybe that's why the action response layers didn't help us. It looks like this thing is actually rich enough to do all of the work of modeling human behavior, and that there's really no reason to be adding iterative reasoning on top of it. So that sort of both excited and bummed us out. I mean, it bummed us out because we were wrong for like 10 years. But it excited us because we would now like to properly do what we originally set out to do, which is constrain, have an over-parameterized model where we constrain a level zero part of the architecture to really be non-strategic and then allow strategic iteration on top of it. And we would get something that's both interpretable and actually conforms to kind of these observations about human play. So that's work that Greg and an undergrad in my group are currently working hard on. And we're hopeful we're going to get somewhere, but that's at the bleeding edge for us. So that takes me to the end of my time with you. So I hope I've left you with the sense that behavioral game theory is something that you need to take seriously if you're thinking about multi-agent systems that involve actual unsophisticated humans. If you're thinking about professional poker players or stock traders or nation states, behavioral game theory is probably not for you. Although if Trump is the leader of your nation state, then you can decide. But on the other hand, a lot of the time we really want to talk about people. And when we're talking about people, I think we really need to take seriously the overwhelming evidence that Nash equilibrium does not predict people's behavior. And I mean, sometimes it does, but it doesn't reliably predict people's behavior. And I think we can do better. It really has been shown that you can learn models from data in a way that generalize even to entirely different strategic situations. Imagine how much better you could do on your problem if you restrict yourself only to some pretty limited domain of problems. You could likely fit a much more reasonable model than what I'm showing you here, which is taking this kind of quixotic task of arbitrary matrix games and trying to do something sensible there. And I think our field can really move forward in this way, and we can really bring the sort of Cold War hyper-rationality of game theory together with the machine learning revolution that has shown that we can do a lot better when we take some data into account. I'll end there, but I've left my 7 questions up here in case anyone wants to take a picture of them. I think I promised you 9 questions, but I was lying. So thanks very much. Yeah, go ahead, please. Sorry, so I'll repeat the question and then ask a clarifying question. So I think you asked, are the shallow models applicable to level 1 and level 2 players? Let me try to understand what that means. So I think the shallow models, you mean things like our linear 4 model that I told you about. That, yeah. So this model is a way of inducing a probability distribution over actions, right? If you think about it, it gives a weight to every action, and then we normalize these weights, and it ends up saying on a given game, here's a distribution over level 0 play on the particular game that I was given. Our level 1 and 2 agents that we fit the models to are fit with respect to that level 0 specification. So when we optimize this thing to data, we're learning the level 0 parameters and the level 1, 2 population percentages jointly. So in the end, and this is a really important point to understand, so thanks for asking the question. In the end, when we change the level 0 model, we're also changing the level 1 and level 2 model because they're responding to something entirely different. And so that's a really powerful and I've found when I talk to people in the past, often misunderstood thing about this approach. So thanks for highlighting that. Tell me if I misunderstood your question, but I think maybe that was it. Yeah. Yeah.
Two quick things. One, thank you for your theory line course. Without it, I'm gonna have half of like.
Yeah, it's a shame. Like basically, this talk is like that was all lies, so that was completely wasting your time. But.
Side of things, and I'm pretty interested about this strategic and non-strategic deep learning architectures. And I wanted to ask, once we move away from just like basic sport games, I wanted to ask what's like where do you draw the line between the strategic and non-strategic architectures? For instance, in my company, Sony AI, we made like deep learning models. We play the game of Gran Turismo, which is a racing game, and we don't do any opponent modeling insofar as we don't have anywhere on the neural network, like let's say like a head that says what is the distribution of actions the opponent will take. We don't do any of that, but we do give, for instance, information about what is the relative speed and position of the other agents to our AI. So would that be considered a non-strategic architecture? Because we're giving information about other agents, and then the neural net will be able to use it for its actions, but we don't explicitly anywhere in the network actually tell the agent follow what the other agents are doing. So what's your thought? If you give information about other agents, information in the world, would that account as strategic or not strategic?
So I guess you can see this whole sort of AR layer, like AR layers, like cognitive hierarchy sort of architecture as a particular form of inductive bias that you might want to put into a model that we have pretty good behavioral evidence for, right? And like by the way, we have very little evidence that anyone plays above maybe level 2, right? Like maybe level 3. Almost no evidence that anyone other than Gary Kasparov thinks more than 3 moves ahead, right? So pretty much what we want to think about is, but it's very hard to not pollute those higher levels with like not to get the like non-strategic thing to sort of like fit that part of the data too. So I think what's really necessary if you want to exploit this inductive bias that says people optimize against beliefs, and optimization is kind of easy to think about. Like quantum best responding is a really simple. It only takes like one node in a network to think about like how do I take some distributional belief and then respond to that in a sensible way. That's really easy to model. The hard part is to make sure that the architecture gets set up in a way where the distribution is really meant to be the distribution that somebody has in their head. And so I think if you use some of these ideas or do something similar that really tries to enforce, like this is what somebody would do if they were really not thinking about other people, then I think you'll benefit from that inductive bias. So partly like I love the work you guys have done in Gran Turismo. I've talked about it many times with like Pete and Peter, and like great stuff. But I guess I would just say maybe you have domain knowledge. Like maybe when people play a driving game, like non-strategic behavior looks like when I see something in the environment, I just hit the pedal without like thinking about other people. Like that's almost surely non-strategic. So maybe in some cases, like when you're doing something like you guys were doing, which is a really big push into a particular domain rather than kind of general purpose basic research, you could leverage things like that. But I would just try to think really clearly about like trying to make a dividing line between level 0 and level 1.
Yeah, thank you so much.
Cool. Yeah. Well, that's so the comment was some people must be thinking to level 0 to infinity if they're saying 0 in in these behavioral experiments. Good point. I mean, I find typically those people are sort of trained game theorists who understand it isn't so much that they're really thinking to the level of infinity, it's they understand how to perform induction, right? So at some point, if you understand kind of the mathematical setup, then but I find normally, like if I talk to somebody on a coffee break afterwards, I can pretty much talk them out of it. And the reason is not so much that they lose the ability to perform induction, but the induction has two steps. You have to yourself know how to think a level deeper, and you have to think it makes sense to think that your opponent is also performing as much induction as you. And usually the second step can cause you to, on reflection, kind of break your commitment to induction, because you really, once I showed you, this thing about the New York Times readers, if I now showed you Traveler's Dilemma, which is another, backwards induction solvable game, but not quite the same structure, I don't think you would again pick the Nash equilibrium. You would start to realize I'm facing a population of people who don't perform induction, so it would be silly for me to do that myself. I don't know if that convinces you, but that's what I think. Anyway, thanks very much for sticking through to the bitter end, and I'll stick around if anyone has anything else to say. Thank you. And thanks to the volunteer for putting up with my stupid laptop. I appreciate it.
Volunteer has done many things throughout the day.
I would say, I mentioned you by name, but you're sitting such that I can't see it. Jose